Yon that will speak about on behalf of the D0 and totem collaboration about the comparison of differentials, elastic cross-section in PP and anti-PP collisions as evidence of the existence of a colorless CO3 gluon state. So please, Christoph.
And do we have recording on, or is it working, or should I wait for recording to appear?
The recording is on, so
okay, cool.
You can start.
Okay. So thank you. So good morning or good afternoon, everybody. So what I will discuss in this talk is the way to see, the existence of the colorless CO3 gluon state by comparing the proton-proton and the proton-antiproton collision. So I will start by discussing what is the Hadron, what do we want to see. I will mention the D0 and the totem data, see how we extrapolate the totem data to Tevatron energy, and finally compare the D0 data and the totem extrapolated data. So first of all, let me, in one slide, very briefly, to explain for people who are not familiar, what is the Hadron. So you have this diagram on the left, which basically consider hadron-hadron interactions. And you see that in terms of QCD, so this can be described by many gluon exchanges. So we talk about gluon ladders that are exchanged. We have, for instance, n of them on this diagram. And this was introduced especially by the people like Bartel, Kwiecinski, and Prasalovich in order to describe elastic proton-proton interaction. So what do we mean by elastic is that the protons are intact in the final state. So now, for concerning the Hadron itself, so there is a definition given by Basarab Nicolescu, who invented, between quotes, the Hadron. And he wrote that the Hadron is defined as a singularity in the complex plane located at j equal 1 when t is equal 0, and which contributes to the hot crossing amplitude. So it may be obscure, for many people, because based on Regge's theory. So that's why on the right, I made a kind of QCD interpretation of the Hadron. So we consider these two diagrams, the lowest diagram. The left one would be the Pomeron, where you see that we have two vertical gluons. And for the Hadron, we have at least 3 gluons that are here. So this leads basically to this contribution that I was mentioning before, 2, 3, 4, 5, and so on gluon exchange in terms of QCD. And the colorless CO3 gluon state, Hadron, predicts differences in the elastic cross-section d sigma dt between proton-proton and proton-antiproton. So this is basically that what we want to look for is this kind of difference between proton-proton and proton-antiproton collision, since they correspond to different amplitude and interference. So before studying the difference, let me discuss very briefly what are the measurements that we are dealing about. So this is, in fact, the elastic scattering at Tevatron and LHC. So you have just a sketch diagram, which is here, which shows you d sigma dt, so the cross-section as a function of t. So what we study is the elastic interaction, so proton-proton going to proton-proton, or proton-antiproton going to proton-antiproton. And there is an exchange of momentum between the two protons, which remain intact. And the idea is to measure this intact proton in dedicated detectors that are called Raman pods, and they were installed both by D0 and the totem collaboration. So what do? We count the number of events as a function of t, where t is the quadri-momentum transferred squared at the proton vertex. Is measured by detecting the intact protons, and by counting the number of events, we can get the cross-section as a function of t. So you see that there is some part that we call Coulomb, which is proportional to 1 over t squared. Then there is what we call the nuclear part, which is an exponential decrease. And there is the interference region between the two. There may be some structures. We will come back to this later. And then at higher t, we reach the perturbative QCD domain, where it can be a power basically of t for the decreasing value of d sigma dt. So now let me introduce briefly which data we are considering for this work. First of all, the proton-antiproton d sigma dt cross-section measurement by D0. So this is the plot which is shown on the left. So D0 collected elastic PP bar data. You have the schematic of the Raman pod detectors on the top. So there were Raman pod detectors to measure proton and antiprotons on both sides of the interaction point on both sides of D0. And they did the measurement actually at the end of data taking of D0 with about 31 inverse nanoband of data, and they were published in this reference. So this allows to measure the elastic PP bar data for this domain in T at 1.96 TeV within the Tevatron center of mass energy. Now, let's come to the totem data. So as you know, totem is at the LHC. So they measure the proton-proton elastic cross-section, and they were measured at different center of mass energy. So 2.76, 7, 8, and 13 TeV. So they are illustrated in these three plots. I put three of them, which are for 2.76, 13 TeV, and 8 TeV. And the idea is basically the same as for D0. We have dedicated proton detectors that were installed close to the LHC around AP5 where CMS is located. They are located as about 200 meters from CMS, and they allow to detect the intact protons in the final state in order to measure elastic events. So now let's discuss a bit the strategy of comparing proton and proton-antiproton datasets, because this is the way, if we want to be able to see this kind of three-gluon state event, we need to be able to compare these two cross-sections. So you have on the left plot the different totem data that were shown in the previous plot, but here on the same slide. So there are the different d sigma dt as a function of t for the four center of mass energy that I mentioned before, 13, 8, 7, and 2.76 TeV. So what do we notice? Is that we have the same features for this proton-proton interaction. It means that we have for all of them a kind of a dip, where you see a minimum of d sigma dt, then a kind of a bump, and then it decreases again. So these are this kind of characteristic properties of proton-proton interactions, which appear again at all center of mass energy, that we want to quantify and try to extrapolate to Tevatron energy, which is 1.96 TeV. Because in fact, where the D0 data do not show this feature of having the dip and the bump. Let me go back once again to this data. So this is the measurement by D0, and you see that we don't see this kind of feature of dip and bump. So this is the basically strategy would be to see how these characteristic properties of PP elastic interactions vary as a function of square root of S in order to extrapolate to Tevatron energy. So the first point that we look at, because this is the most obvious, this is the bump over dip ratio. As I said, for all totem data, we see a bump and also a dip. So what we show on this plot is the ratio bump over dip as a function of square root of S. So you have on the left in pink all the ISR data. So this was before Tevatron and the LHC at lower energy. You have the totem, the 4 points in black with the uncertainties. And then you see the singular point, which is here in blue, correspond to the D0 measurement. So what we see is basically, we see a flat behavior, let's say starting at 100 GeV up to 10,000 GeV, so LHC energy. So we have first this ratio R which decreases, and then it's getting flat. Whereas the PP bar shows the ratio of 1, given the fact, again, that no bump or dip is observed in the PP bar data. So it means that we have more than 3 sigma difference already at this stage between PP and PP bar elastic data. But we wanted to go a bit further because, as you see, I mean, there is no measurement between something like a 700 GeV, 70 GeV, sorry, up to 2000 TeV. So there is an area here without any data points on PP data. And that's why we wanted to have a better analysis, because maybe something might happen in this region when we assume something flat, but we have no way to prove that it's indeed flat in this region. So that's why we wanted to do a more detailed analysis. And this is based on the reference point that I discussed before. So what is it about? This is illustrated on this plot, which is here. So you have the 2 points, which are completely obvious. So this is the dip and the bump. So I forgot to mention this corresponds to d sigma dt for any square root of S for proton-proton interaction as a function of t. So again, the dip and the bump are 2 obvious points. And then we defined other points that we call characteristic with respect to the shape of the feature of the behavior of d sigma dt, elastic d sigma dt at high energy. So what are there? For instance, you see that we can have the same value of the cross-section at another point. It's called deep B. We can take the points that are in the middle between the bump and deep B. So this is what we call mid 1 and mid 2, which are here. Then we have the value, same value of the cross-section as the value of the dump at lower values of t. So this is what we call the sigma dt at bump. And then, since here we have a fast decrease of the cross-section as a function of t, we take 5 times the distance in vertical axis between the dip and the bump in order to get bump plus 5. And if we take it 10 times, we are getting bump plus 10. So this is why these are the 8 characteristic points that we define that represent the feature of elastic d sigma dt. And I should mention that we don't try to do any fits of the data. We want to be as close as the data as possible. So we use the data points that are closest to those characteristic points, because of course, for instance, if the measurement is not exactly at the bump, but you have 2 data points which are around the bump that were measured, we take the point that is closest to the bump. In case the 2 points are very close, we just merge the data bins. And this will give us a distribution of t and d sigma dt values for all the characteristic points. Because for all values of square root of s, we have, for instance, here the value of the bump. We measure what the value of t for the bump and the value of d sigma dt for the bump. So this gives us a series of points that varies as a function of square root of s. So then what we do is to fit all these reference points using these 2 formulas which are here, t as a function of square root of s with a logarithmic scale, and the sigma dt, which is directly proportional to square root of s. I will show you the slides, the curve in the next slide. And basically, the same form is used for the 8 inference points. I want just to stop 1 minute there. You will show again the fits in the next slide, but this is something that was not obvious from the first principle, that all the 8 reference points that I showed before can be described with the same dependence of square root of s. And you will see that it gives a very good fit, and it works for all the characteristic points. So why do we choose such a simple point? Because we have basically at most 4 points to be fitted, since totem has 4 square root of s values, and we have directly the square root of s dependence, which is here. So we cannot have, of course, a complicated fit, since we have only 4 points to be fitted, and they correspond to this 4 square root of s, which is here. We also tried, of course, alternate parametrization, and they lead to similar results, and it leads to a very good chi-square per degree of freedom, better than 1 for most of the fits. And then from these fits, we will be able to predict the position of these characteristic points at 1.96 TeV, which is the Tevatron center of mass energy. So this is the plot which is shown here. So on the left, we have the T values of these characteristic points. You see these circles, they correspond to the measurement of totem. And these are the 8 points that I mentioned before, deep 2, mid 2, bump, and so on and so forth. And the extrapolated value, which is the star at the Tevatron center of mass energy. And on the right, you have the same result, but for the sigma dt, so basically the vertical scale, which give you the elastic cross-section. Again, for the different points, and these points are shifted, so that we are able to see their value by the quantity which is in parentheses. So again, we do the same. We fit the totem points, which are the circles, and we extrapolate to the value which are Tevatron energy, which are represented by the stars. Okay, very good. So now let's see what we need to do in order to compare with the value of the sigma dt that were measured by the zeros or for pp bar interactions. So what we need to do this is to predict what will be the proton-proton elastic cross-section in the same T-bins, basically, as they were measured by D0 in order to make a direct comparison. In order to do this, we need to fit the reference point that are extrapolated to 1.96 TeV from totem measurement. Let me go back 1 slide to illustrate this. So what we have now is this kind of distribution, all these points, basically, which were extrapolated to the same energy as the D0 measurement, but from totem data, so for proton-proton interaction, and we want to fit them in order to compare directly with D0. So what we use for this is the formula which is shown in red. This is what we call a double exponential formula. And it gives a very good chi-squared of the extrapolated data, which is about 0.6 per degree of freedom. I would like to say that this function is chosen for fitting purposes only. I mean, it's not really based on theory. The first function can describe the low T behavior, so the diffractive cone. And the second function, which is here, can describe the asymmetric structure of the bump and the dip. And the two exponential terms, they crossed around the dip. One falls rapidly and becomes negligible in the high T range, whereas the other one rises off the dip. So in order to treat also in a consistent way all the systematic uncertainties, we evaluate them for an ensemble of Monte Carlo experiments in which the cross-section at the 8 points are fluctuated randomly according to a Gaussian distribution. And we put some constraint on those fits because, of course, I mean, the fits should show the properties that are originating from the totem extrapolating data. So this means that only the fits showing a bump and a dip within the uncertainties in the T location predicted by extrapolated totem data will be permitted. And also we have a constraint on the slope and the intercept of the first characteristic point in order to keep the fits which make sense, basically, because they need to respect the properties of the extrapolated totem data. And I should mention, I mean, in parentheses, that the Church formula was chosen also because it leads to a good description of totem data in the deep bump region as 2.76, 7, and 8, and 13 TeV. Okay, good. So now there is the last point, so it's a bit complicated, but the last point is that you know that, of course, the D0 measurement and the totem extrapolated data might have a different normalization. Simply, I mean, saying, for instance, that there is an uncertainty which is related to luminosity. It's, of course, completely independent between totem and D0 data. So, and we need to take this into account and take into account both these kind of effects. So the differences in normalization are taken into account, first of all, by adjusting totem and D0 data to the same cross-section at the optical point. Why do we do this? Because we want to separate the comparison of the shape between the D0 measurement and the totem fit that we presented from the uncertainty due to the normalization, taking, of course, into account the uncertainty like luminosity or correlated uncertainty. So that's why it's important to normalize both sets of data to a given point, and we choose this point to be the optical point, which is the differential cross-section at t equals 0, in order to compare directly the shape of both data sets in the first part of this study. And I just put a short remark, like this optical point cross-section are expected to be equal if there are only C-even exchanges, so basically without any Hadron, and if there is an Hadron, even in maximal model, the difference will be very small. But this is something that is taken into account to systematics. So the way we need to do it is, first of all, to predict the proton-proton total cross-section from extrapolated fit to totem data. So it's illustrated on this plot, which is here, which shows you the total cross-section for totem in the black points, the fit, which is given here, extrapolated again to 2 TeV. So this leads to an estimate of the PP total cross-section at 1.96 TeV of this value of about 82.7 millibar. The next step now is to adjust this cross-section coming from extrapolated totem data to the D0 measurement. So from the totem proton-proton total cross-section that we just mentioned now, we can obtain d sigma dt at t equals 0 using this formula, which is here. So it relates the total cross-section squared to the slope of d sigma dt at t equals 0. This is dependent, a very weak dependence, in fact, on the rho parameter, which is here. So for this, we took the same value of rho as from the compete parametrization. And this leads to a totem d sigma dt at t equals 0 as the optical point of about 357 millibarn per GeV squared. D0 measured this quantity to be about 340.8 millibarn per GeV squared. So we rescale the totem data to the D0 value by the factor, which is 0.954. And I want just to make a side remark here, because you say, I mean, come on, I mean, we cannot extrapolate like this the sigma dt down to t equals 0, because there is a full range close to t equals 0 where there is no measurement. So that's why we do not claim that we performed a measurement of the sigma dt at the optical point at t equals 0. This would require additional measurements closer to t equals 0, but we use both extrapolations in order to obtain a common and somewhat arbitrary normalization point. It means that we normalize both data sets to the same value, and this value are not the meaning to be the sigma dt at t equals 0, but it was important to normalize both data sets between each other. So this leads basically to the points which are here. So the blue points correspond to the T0 measurements, and the red curve correspond, you see that there are some angles, so they correspond basically to the totem predictions after the fits, which are here, and they are just related by straight lines at the same values as the D0 T-beams. So, and you see the dashed line correspond to the 1 sigma uncertainty band. So now we have all the tools to be able to compare directly D0 and the totem data. So let me discuss this. As we said already, in order to compare the both data sets, we have two steps, the differences in shape and also in normalization. So in order to compare the shape, we normalize it to the same absolute value, as I mentioned already, and we perform a Kolmogorov-Smirnov test, which is sensitive to the difference in shape. For this, we produce about 100,000 Monte Carlo pseudo-experiments. They are generated in which the cross-sections are allowed to vary randomly within these uncertainties. The supremum value of the Kolmogorov-Smirnov test is 0.0791, which means it's a probability of 1% for the proton-proton and pp bar cross-sections to be of the same shape. Corresponding significance is about 2.3 sigma. In addition to this, we compare this normalization within uncertainties. And if we compare the pp and the pp bar integral of d sigma dt in the same t range, basically in the t range of the fit of between the dip and the bump, it leads also to a 2.1 sigma effect corresponding to a p-value of 1.7%. So it means that the combined significance of these two effects is larger than 3 sigma. So this means that basically we have some evidence that the colorless C-odd 3-gluon state or the Hadron is needed to explain elastic scattering at high energy. We show that the pp and pp bar data are incompatible within 3 sigma in the deep and bump regions where the effect of the Hadron are supposed to occur. So this brings me to my conclusion. So we perform a detailed comparison between pp bar, so which is 1.96 center of mass energy from D0, and proton-proton interactions with 4 center of mass energy from totem, so 2.76, 7, 8, and 13. The R ratio of the bump over dip shows already a difference of more than 3 sigma between D0 and totem, again assuming a flat behavior above a center of mass energy of 100 GeV, because there is no more data between 100 and the Tevatron energy. That's why we had to do a more complicated analysis of the data. The idea was to fit 8 characteristic points of elastic proton-proton d sigma dt, such as the B, the dip, the bump, etc., as a function of square root of S, in order to predict proton-proton data as 1.96 TeV. This allowed to make a quantitative analysis, which is model independent, in a way that we didn't use any special model to describe the evolution in order to predict the pp cross-section at 1.96 TeV. And we obtained that the proton-proton and proton-antiproton cross-section differ with a significance over 3 sigma in a model independent way, and thus provide evidence that the colorless C-odd 3-gluon state, i.e. the Hadron, is needed to explain elastic scattering at high energy. So this is one of the first time that we have really a clear proof of the existence of this kind of 3-gluon state. And there is a public note, which is a release that will be soon submitted to PRL, and it's available at this web address if you want to get more detail about the analysis. So thank you very much.
Thank you for this very interesting talk and these, let's say, pointy conclusions. I see that there is Marek with raised an hand. As usual, Marek, you are my best customer, so please go ahead.
Just a short comment, Christopher, that the idea that multi-gluon exchange can be responsible for things like Pomeron and Oderon was done approximately 5 years earlier than the people that you quoted. It was done by Nusinov.
Ah, okay. Sorry for that. Can you send me the reference by email, and we will add it in the paper? Yeah, of course. Thank you, and sorry for that. I mean.
Okay, I have actually a question about the experimental analysis, because I mean, it's true that you have a significant around 3 sigma, so more than 3 sigma, but not so far away from 3 sigma, that this bump to deep has a difference, but somehow it's not 5 sigma or 6 sigma, right? So I was wondering, like maybe you can go to, yes, the final figure with the fit where you were mentioning.
Kind of a money plot. Yes.
Yeah, exactly. Here, I mean, if I look at the data, right, it seems rather flat to me. I mean, if I would not know anything, I would not see a deeper maximum, right?
Yes.
And with this data, one can for sure, let's say, calculate also like lower bounds and upper bounds. And the question is, can these, let's say, lower bounds and upper bounds help you, let's say, constraining also a bit more quantitative, a bit more on the quantitative sides, the physics you are looking for? If you, I mean, because you just quoted the deviation, okay, it's clear. But if you take now, for example, the experimental data with the statistical error, systematic error, you can for sure draw like 1 sigma, 2 sigma bands, and then you have like really a lower bounds and upper bounds.
Yeah. And this is what we tried also, of course, in the preliminary version of this analysis, comparing the bond, and it was about the same value. I mean, reaching the same difference. What we still need to try, I mean, it may lead also to something better, is since now we have the fit, I mean, it's comparing directly the slope also.
I see.
Clearly, there is a kind of change of slope, which is completely obvious from the extrapolated totem data. And there is not this change of slope, which is observed with the D0 data. So this is another comparison that we still need to do. And this may lead something which is even more above than 3 sigma. Let's see. I mean, we are just this is in progress.
Okay. And maybe, yeah, I see another end, which is up, Fars or Fairs, or I don't know how to pronounce your name. I'm very sorry.
Yeah.
Please, go ahead.
Yes, hello. Yes, it's Fares. So, hello, Christophe. So you basically showed that the PP and PP bar cross sections, elastic cross sections, were different in certain range. But what I do not understand is it can be from any unknown phenomenological thing from QCD or whatever. What is the relationship with the Oderon? This is really not clear at all for me.
Yes, so this is of course a question which will be more for theorists, and it's a question we had, in fact, for all the people who are doing some model of elastic scattering, I mean, at high energy, and there are not that many possibilities to explain the difference between proton and proton-antiproton. That's why all the theorists so far to whom I asked this question, they all told me that observing a difference in the deep and the bump region on the elastic scattering between PP and PP bar would be the cleanest possible signature of Oderon. I am not saying that some people might not come with another model which can be more complicated, or I don't know, that could explain the difference without any Oderon, but this would not be natural. This is what I mean, again, I'm not a theorist, so I don't know the detail, but this is something that was agreed by all people working on elastic scattering in this kind of high or medium T region, and see the dump at the beam the bump and the dip region. And they all come with that conclusion that the difference will be one of the clearest possible signs of the existence of the hadron, because it would be difficult to explain it in another way, let's say. So I don't know if it answers completely your question. But,
okay, this means that I have to read a little bit more about it.
yeah,
okay, thank you.
Myself also.
Yeah, thank you.
Okay, so are there other questions or comments? Okay, I don't see any reason end anymore. So thanks a lot, Christoph.
Thank you.
We
so
can
stop sharing.
Yeah, you can stop sharing, and then we can go to Piotr. The next speaker of this session is Piotr Lebidovich. We'll talk about searching for hadron exchange in exclusive PP and PP2-Phi and PP2-Phi-Phi reaction at VLHC.
Yes, hello everyone. I will present new results on central exclusive production in context of searching for soft hadron based on works in collaboration with Antoni Szczurek and Otto Nachtmann. As Christoph mentioned, a hint of hadron was seen in ISR results as a small but significant difference between the differential cross sections of elastic proton-proton and proton-antiproton scattering in the diffractive deep region at center of mass energy 53 GeV. The interpretation of this difference is however complicated due to non-negligible contributions from secondary regions. So, as was presented by Christoph, new totem results combined with the zero observation provide further important evidence for the hadron exchange. The charge conjugation C-1, C equal -1 counterpart of the C equal +1 pomeron. So to clarify the status of the still elusive hadron, clearly it is of great importance to study possible hadron effects in reactions other than proton-proton elastic scattering. Here is general diagram for central exclusive production in which different exchange objects can participate. In my talk, I shall consider soft exclusive processes in non-perturbative framework as a source of information for soft hadron exchange. Okay, for this purpose, we use the model in which the pomeron exchange can effectively be treated as exchange of rank 2 symmetric tensor with corresponding propagator, with tensorial structure and vertices. And the hadron exchange as effective vector exchange. Here we assume linear Regge trajectories, and for simplicity we use electromagnetic Dirac form factor of the proton. Applications of the tensor pomeron and vector hadron model were given for photoproduction of pion pairs and for number of central exclusive processes. Photoproduction is suitable reaction for hadron search as there will be interference between two processes leading to pi plus, pi minus charge asymmetries. Here I would like to draw your attention to tomorrow's talk by Otto Nachtmann on axial vector meson production via pomeron-pomeron fusion. For single phi meson production at high energies, two processes should be considered: photoproduction diagram on the left and hadron-pomeron fusion diagram on the right. As I will show later, at relatively low center of mass energy of WA102 experiment, we have to include also some contributions with Regge's vector meson on the region exchanges. The Born level amplitude for photon pomeron fusion is written in terms of tensor pomeron propagator and effective vertices derived from Lagrangian, from coupling Lagrangian. Inclusion of photon is straightforward here, and gauge invariance is guaranteed. For the pomeron phi-phi vertex, but also for the pomeron hadron phi meson vertex, we use an ansatz analogous to F2 tensor meson photon vertex. This vertex is parameterized by two independent couplings, A and B, with corresponding tensor structure functions. T dependencies are described by the form factor with cutoff parameter. The model parameters of photon pomeron contribution are fixed to describe the Hera phi meson photoproduction data. To illustrate this point, here we present elastic phi photoproduction cross-section as a function of center of mass energy, left panel, and the differential cross-section, right panel. Our results, including omega phi mixing effect in final state, nicely describe ZEUS data at 70 GeV and low energy experimental data. Here, the Pomeron exchange is dominant contribution. We show results for two parameter sets, set A and set B. The latter one describes region of larger T better. In the case of Oderon-Pomeron contribution, we choose as default values Oderon intercept close to 1, slope of trajectory such as for Pomeron, and eta parameter to be -1. In the proton-Oderon vertex, we assume that the Oderon-proton coupling is 10 times smaller than proton-Pomeron coupling. Anyway, to fix the strength of Oderon, here we shall discuss the WA102 data. It should be emphasized that we include in our calculations absorptive corrections in the one-channel eikonal approximation on the amplitude level. It's very difficult to describe phi dependencies measured by WA102 collaboration at lower center mass energy, including the photoproduction mechanism only. Here, phi is azimuthal angle between transverse momentum vectors of outgoing protons. Here we show results for various fusion processes, including interference effects between them. From the right panel, we see that inclusion of the Oderon exchange contributions significantly improves the description of data. The same observation is true for called DPT variable. So with suitable parameters, we describe the low energy data. Then with model parameters adjust in such way, we made predictions for LHC experiment. In contrast to low energies at LHC, the Oderon exchange contribution competes only with the photoproduction mechanism. Here we have results for phi meson production in K plus K minus channel. For experimental condition relevance for ATLAS, with cuts on leading protons for alpha detectors. Shown are distributions in transverse momentum of the proton, in azimuthal angle between outgoing protons, and in rapidity, distribution in rapidity difference between kaons. Due to the alpha limitations on the forward scattered protons, the photoproduction term is strongly suppressed. And in addition, absorption effects for both photon-Pomeron and Oderon-Pomeron contributions is similar size. Clearly, different behavior is seen for both contributions. Even if true Oderon contribution should be smaller by a factor of 2, the distribution in rapidity difference between kaons seems particularly interesting. The different behavior of two contributions here can be explained by studying angular distributions of kaons in the rest frame, for example, in the Collins-Soper frame. These angular distributions give information on the polarization state of the produced phi meson. We found that photon-Pomeron fusion leads predominantly to transverse polarization, while Oderon-Pomeron fusion shows clearly longitudinal phi meson component. Here are results for LHCb kinematics at forward rapidities and without measurement of protons. And therefore, here the absorption suppressed mainly the purely diffractive term. However, for larger kaon transverse momenta or transverse momentum of K plus K minus pair, the Oderon contribution is bigger than the photon production term. Now let's look at second reaction in which the phi resonance decaying to muons. Here we have the muon invariant mass distributions in the phi resonance region. In addition to the resonant contributions, here we discuss also the continuum term. From our predictions for this reaction for LHCb kinematics, we can see that imposing a larger cut on transverse momenta of muons reduce the continuum contributions. This is the dotted black line, which however still remains sizable at rapidity difference equals 0. Note that in the contrast to the kaon production, here is there is for both the photon-pomeron and the Hadron-pomeron fusion contributions a maximum at rapidity difference equals 0. So the muonic channel seems to be less promising in identifying the Hadron exchange, at least when only the PT muon cuts are imposed. Our results shows that the low PT cut on transverse momentum of the muon pair can be helpful to reduce unwanted continuum and photoproduction terms. However, such cuts strongly reduce then the statistic of measurements. In my opinion, a combined analysis of both K+, K- and muonic channels should be the ultimate goal to search for Hadron exchange. Another interesting reaction is diffractive double phi production. Here we focus on 2 to 6 processes as arising from 2 to 4 processes, taking into account the spectral functions for phi mesons, to include smearing of the phi meson due to the resonance distribution. At high energies, the pomeron-pomeron fusion processes are dominant production mechanism. At low 4 kaon invariant masses, resonances, for example, tensor blue ball production are expected to be important. But at higher masses, continuum terms with intermediate charge conjugation -1 exchanges should be important. So contribution with an intermediate Hadron would give the leading term if its intercept is higher than normal C-1 regions. Let's go to the results. Left panel shows our results together with the WA102 experimental data for double phi production. In our model, we include F2 resonance contribution at the continuum processes for the Regis phi exchange and for Hadron exchange, the red line. For the Regis phi exchange term, we adjust couplings and form factors at lower invariant masses. For the Hadron exchange, we use the parameters found from single phi meson production. The coherent sum of all terms is shown by the black solid line. Figure on the right shows our predictions for LHC-B experiment. If you look at these figures, you can see that the phi exchange contribution, the short dash line, steeply falling with increasing invariant masses. Therefore, an Hadron with intercept close to 1 should be clearly visible in the region of large 4 kaon invariant masses outside of the region of resonances, and also for large rapidity distance between phi mesons. So this is also a very interesting clear signature for search for Hadron. This brings me to my conclusions. So we consider 2 exclusive soft processes as possible source for Hadron exchange within the tensor pomeron and vector Hadron approach. Having fixed the parameters of our model to the low energy data, we make predictions at LHC. In my opinion, several distributions should be studied and in different channels to draw definite conclusions on the Hadron exchange. For single phi production in K+, K- channel, the distribution in rapidity difference between kaons seems particularly interesting. In muonic channel, to observe sizable deviation from photoproduction, a cut on transverse momentum of muon pair seems necessary. For double phi production, the Hadron contribution should be distinguishable from other contributions in the region of large kaon invariant masses and for large rapidity distance between the phi mesons. We expected here so-called free gap events. So we are looking forward to first experimental results on single phi and double phi central exclusive production at LHC. Thank you for your attention.
So thank to you for this nice talk. So are there questions or comments? So I have one then. So, yes. And I was wondering, so I know there is one by Rona, but I will ask my question briefly. So now what can happen in the final state is actually that you also have some final state interactions, and these can deform a bit your invariant mass spectrum. I mean, not particularly, maybe not up to these tails with large invariant mass, but you could have deformations. Did you consider that in the final state, proton and phi can undergo final state interaction?
So this is very important question in context of the final state interactions between centrally produced mesons, for example, for chaos, as for example for this process.
Okay.
Yes, we in our model we include in approximate way only absorptive corrections in proton-proton initial and final state between protons. But
okay.
Important to include to extend our model.
We also include chaos. I see. There are 2 questions, so maybe we can go quickly through them. Ronan was first. Please go ahead. Ronan, can you hear us?
Yes, can you hear me okay?
Yeah, now it's good. Please go ahead.
Hi, Piotr. Very nice talk. So we already saw from Christoph that there's some small evidence possibly for Hadrons coming from the elastic scattering data. And if there's an Hadron consistent with that data, would that same Hadron be visible in what you're looking for? Or are they different kinematic regions that one is sensitive to?
So we are mostly interested in the soft Hadron, in this sense that in the regime of non-perturbative framework. So especially soft exclusive processes are a nice framework to search for such effects as soft Hadron. In our model, we roughly estimated coupling of Hadron to protons from comparison to PP and PP bar elastic scattering to 10 times smaller than Pomeron to protons. So the strength of the Hadron is really small, but we think that the good opportunity is to look for different processes and different differential distributions. For example, angular distributions to search for signal for Hadron.
Okay, I think that we have to move on. And Anthony Surek can maybe...
Okay, thank you. I have a comment to both questions because you asked the question, phi very weakly have final state interaction with protons, for instance. Phi very weakly interacts with something else. So this is to the first question.
Couplings are smaller, yes, smaller with all objects.
So you are right for other channels, but phi is specific where final state interaction is small. And to the second question is, Piotr partly answered this because this coupling is taken to be consistent with this Atlas data. However, we cannot say anything about coupling of Pomeron, Hadron, and phi. This is something which we cannot answer from first principles.
Yes, we try to fix this coupling to low energy data and give predictions for LEC. So we should be looking forward to first experimental results on phi and double phi at LEC.
Okay, so, Piotr, thanks a lot. I'm sorry, but I have to cut the discussion because we are running late. Very nice talk, but we thank you again.
Thank you.
And then we move to the next speaker, who is Oliver Surani. I'm very sorry. I mean Surani.
No problem. No problem.
And Oliver, who should share his slides because otherwise we cannot see them.
Okay, just...
We'll talk about central, exclusive, and diffractive physics measurement at CMS and Totem.
Okay. Okay, do you see the slides?
Yes.
Okay, so then I will go on. So thank you for the opportunity to have me on ICHEP. My name is Oliver Surani, and I'm from Budapest, Hungary, from the Utrecht University, and I will talk about CMS and totem central exclusive and diffractive physics measurement. And in particular, I will talk about these two measurements, the central exclusive dipion production at 5.02 and 13 TeV. This is a CMS only analysis, which was recently accepted for publication at EPGC. And the second part will be the diffractive digest with proton tagging at 8 TeV. This is a CMS plus totem common analysis. Okay, so the first part is kind of similar to what Piotr talked about in the previous talk. So basically, we were studying the central exclusive production of dipions in proton-proton collisions, in which the two dominant processes are the double pomeron exchange, when two pomerons are exchanged, and the vector meson photoproduction, where quasi-virtual photon fluctuates into quark or anti-quark states and scatters with via pomeron with the other proton, and the vector meson is produced. The quantum numbers of these intermediate particles, well, not really particles, but states, defines the possible final states. So they can, the observation of these processes can act as a quantum number filter and filter certain low mass resonances, giving an opportunity to study them. This also provides a gluon-rich environment in the double pomeron exchange, which is also suitable for global change, although this is not the topic of this talk. This central exclusive dipion analysis was performed on a 2015 low pileup data at two different collision energies. The events were collected by zero bias trigger, so basically just random bunch crossing, no conditions are applied at the trigger level. On the other hand, on the event selection, we have several event selection criteria, so we require exactly two oppositely charged pions, which we identify as pions via their DDX. We also require no activity in the calorimeters, so we can ensure the exclusivity of the events, except of course a cone around the extrapolated heat of the tracks in eta and phi. And also we have these kinematic constraints, so all the results will be meant in this kinematic region. I mentioned we use DDX for particle identification. We fitted the logarithm of the energy loss, so the distribution of this value in momentum slices with Gaussian distributions, and we use a 3 sigma band for the pion identification. Below 0.3 GeV and over 2 GeV, we considered everything as a pion. This leads to a large kaon contamination, but we treat this in the analysis and do a background subtraction. Okay, just a few words about the backgrounds. In this analysis, we have the so-called multi-hadron or multi-particle background, when we have the identified pion pair, and beside that some undetected extra particles. And we estimate this background contribution by considering events with some extra calorimeter activity, and we can construct a background template from these events. This is denoted by these red contributions, and we can calculate the normalization by checking the same distribution from same sign tracks. Of course, in same sign we only have background events. We don't have signal, so the ratio should be. Our assumption was that this ratio should be the same, and of course we can change this background control region to check the systematic uncertainty of this background subtraction. So here you can see the shape of the background distribution and pi plus pi minus mass, PT, and rapidity distributions, and also the two background contribution, the multi-particle and exclusive K plus K minus, and also proton-antiproton background. So we subtract this contribution, and therefore we come to the final results. These are the differential cross-section as a function of invariant mass, as a function of dipion transverse momentum, and the function of dipion rapidity. We do a comparison to two Monte Carlo simulations, the Starlight, which models only this vector meson rho photoproduction, and the DIME MC, which only models the non-resonant continuum double power and exchange contribution. Until the point of this publication, there was no simulation available to describe these low mass resonances. However, we know that there are plenty of them in development. Maybe some of them are already available. And of course, we integrated over these spectra and measured the total cross-section. This is also meant in this kinematic region, of course. This is 32.6 microband for 5 TeV and 33.7 microband for 7 TeV data. Let's have a look at the invariant mass spectrum. We can see an enhancement in the row 770 region, as also predicted by the Starlight contribution, and we see a sharp drop around 1 GeV in the cross section. This was seen by previous experiments as well, and this is generally considered as an indication of the F0980 resonance. And the reason for this sharp drop is an interference between the resonance and the continuum. We can see a very significant peak around 1200 MeV. This is this F2 resonance. Yes, let's go on. And we made a very simple fit to this mass distribution, where we sum the resonance and the continuum amplitudes, and took the square of it, so therefore absolute value square. Therefore, we can introduce the interference terms in this model, and theory results predict that the interference between the vector meson and the double Pomeron exchange sector is smaller than 1%. So we choose the terms that to have no interference terms in this field between these two processes. Yes, they include, these amplitudes include relativistic Breit-Wigner amplitudes for spin J resonance. And the fit results are shown here. 4 resonances were used in this fit. This F0 500, this rho, F0 and F2 resonance. And we can see that we can have a pretty good description of the observed mass distribution. And from that, we can also extract the resonance yields. Okay, let's go to the second part. I guess it will be a bit shorter part. The single diffractive dijet production. So the observation of single diffractive dijets with the tagging of protons. So in case of a single diffractive process, we also have this Pomeron involved, or not only Pomeron, but this can be also Region. And we expect a rapidity gap around the proton. And in case of hard diffraction, this process can be described according to the factorization theorem, which states that the cross section can be calculated by the convolution of.
Sorry, Olivier, I have to tell you to speed up because you had only 15 minutes and your time is up really. So if you could.
Okay, sorry, didn't I started at 4:20?
Yeah, but you have just 15 minutes in total. Also.
Okay, with the questions.
Yeah, so that's
why.
Oh,
sorry, then I will go quickly through it, sorry.
Yeah, I just wanted to warn, okay.
Okay, sorry, I thought I have 15 minutes, sorry. Okay, so this factorization theorem is spoiled by software scattering effects in hadron collisions. I think I will skip this slide then about totem detectors because I think they were already mentioned. There was already a talk about totem. What is important from here, these 3 quantities, the forward momentum transfer and the fractional momentum loss. This measurement was done in low pile-up PP collisions at ATV in 2012 with special beam optics of 19 meter beta star. At trigger level, dijets with PT larger than 20 GeV was requested, and that at offline we requested 2 jets with PT larger than 40 GeV and eta smaller, absolute value of eta smaller than 4.4, while reconstructed primary vertex. The position of the proton in the ρ1 pot is also restricted to have high efficiency, and we also reject elastic events by rejecting 2 protons with a back-to-back configuration, and we also have a kinematic region defined here. Non-diffractive dijets are modeled with PTA6 and PTA8 with different tunes. Diffractive dijets with PTA8, and with these two tunes, and also this dynamic gap model in which this survival probability is modeled dynamically. On the other hand, we have POMVIG, which is based on Herwig 6. And in that case, we only have a constant survival factor. But on the other hand, this POMVIG also models region exchanges. And of course, the full detector is modeled in GEANT, and the beam protons are also transported to the Roman pods. Okay, so quickly, I have only 2 slides about the results. The spectra are unfolded with iterative D'Agostini method. We can see that this PTI dynamic gap model and the POMVIG gives a good description when the POMVIG is multiplied by this survival probability extracted from the data, by the PTR4, 8, 4C, and QTP8 and 1 tunes predicts a higher contribution. Okay, we also have the ratio of single diffractive digests versus the inclusive dijet cross-section. We generally have a large deviation at low PT, low X, low X range. The POMVIG and the PTI8 dynamic gap model gives a good description, although they also have problems at this low X region. And on the right plot, we can see a comparison to the same quantity measured in CDF, and we can see a decrease compared to CDF results. And this is a feature that was already seen in CDF, so they have had a smaller center of mass energy measurement, and though it's not shown on this plot, but they already see this decrease in the cross section. So just a very quick summary, I presented these 2 analyses about exclusive dipion production, and the second one was this diffractive dijet production with proton tagging at 8 eV, which was a joint effort of CMS and Totem. So thank you for your attention, and sorry for...
Oh, thank you very much. In the end, it was so a couple of minutes late, but I see there is a Rafael that want to ask somebody something. So please, Rafael, quickly.
Yes, can you hear me?
Yes.
Yes.
Okay. Hi, Oliver. Nice talk. I will have a comment regarding slide 14, where you show the fit to the invariant mass spectra. So you say that you extracted yields of resonances, and when I went through the paper on arXiv, I can also see that you do not mention anything about the extrapolation to the full geometrical, full solid angle, because you clearly have on the plots the cuts on PT and eta of a single pions, which change the line shape of the bright Wigners that you fit. And in my opinion, it introduces systematic bias to the results that you get, not correcting for the angular acceptance of the detector before making a fit. So in my opinion, the yields that you have extracted are biased and underestimated. Have you a comment on this?
Well, we haven't done the extrapolation. So basically, yes, this might be biased.
Because I hope you understand that, for example, the pi plus pi minus pair can be produced nearly at rest, and then if it's low mass, the decay products, the single piots may not have either PT above 0.2 GeV, or they may just escape the very forward region of the CMS, right, where you have no acceptance. So, I'm curious if any referee that you say accepted had a comment on this.
There was no comment on this from the referee.
Okay, thank you.
Okay, so thank you very much again for the talk. Then we move to the last speaker of this first part of the session, with Sylvester Giossen, and he will talk about the overview of the Electron-Ion Collider physics program. So please, Sylvester, share your slides.
Hello, can you hear me?
Hi. Yeah, sure, very good.
Great. Okay, and can you see my screen?
Yes, we can.
Okay, great. So I'm very excited to be talking to you about an overview of the full Electron-Ion Collider physics program, where I'm really focusing on the science highlights for the EIC, because there's of course a very long program, a very rich program at this point that I would not be able to discuss in half an hour. So in January of this year, we got the very happy news from the Department of Energy that they had selected a site for the Electron-Ion Collider. And this actually contained two pieces of news for us. One is, of course, that we could finally start designing our detectors and our accelerator not based on two proposed locations, but on one specific location. But the other one was that apparently a month before they had given us they had made the CD0 decision, which is essentially DOE saying that there is a mission need to construct this device. They announced that EIC would be constructed over the next 10 years at an estimated cost between 1.6 and 2.6 billion, which really, moves this project into the next phase where we're really starting to get ready to build this machine over the next years. So it's very exciting. So what does the EIC at BNL look like? Well, it's a high luminosity and high polarization electron-ion collider. It will be able to accelerate electrons between 5 to 18 GeV and polarized protons between 40 and 275 GeV. It will also be able to accelerate light and heavy ions with energies between 40 and 110 GeV, and polarized light ions with energies between 40 and 184 GeV per nucleon. The accelerator has room for two large acceptance detectors with detector elements that are integrated in the accelerator interaction region for forward detection. There is a very wide coverage of center of mass energies, and the estimated time that we would start, when the project would be completed and we could start taking data, is of the order of 2030. To the right, you see a picture of what the EIC will look like, and we will be able to recycle two of the existing accelerator rings from RIC for the ion ring and possible ion injector ring, and build a third accelerator ring in there to store the polarized electrons. EIC will really be a unique machine. It will be the world's first polarized electron, polarized proton or light ion collider, and it will also be the world's first electron-ion collider in general. You can see over here on the two figures, which on the left show the current polarized deep inelastic scattering data available, world data, and show in two bands the EIC in two of its configurations and how it will incredibly enhance our phase space for this process. And the EIC here is very unique in that we'll be able to go from very deep in the C region to all the way into the valence region. In the right figure, I show the available data for electron ion scattering or muon ion scattering, also overlaid with how much the EIC will expand our knowledge of the available phase space in X and Q squared. Right now, we are very actively defining our detector concepts that we will build to make out our two detectors, and to make sure that these detectors will be able to deliver our very ambitious physics goals for the electron-ion collider. So right now there are four there's 4 concepts that we're talking about, although there's a very active effort ongoing in the EIC users group to come to some new next generation concept detectors. The base detectors that we're starting off is on the left top, you see a Jefferson Lab designed for a detector, which uses the Clio solenoids to build this detector. At the right top, you see what could be a zero-day detector for EIC, which is essentially an evolution of the Phoenix detector. In the left bottom, you see the argon topside concept, which has this concept that we use ultra-fast silicon for particle identification to simplify the barrel region. And in the right bottom, you see the BNL Beast concept detector, which uses the Babar solenoids. All of these concepts have in common that they are very hermetic detectors. They have beamline. They are completely integrated with interaction regions. So you have far forward detectors. You also have far backward detectors for low momentum electron tagging. All 4 concept detectors also have excellent PID in essentially the 4 pi region, where we have both neutral and charged particle identification. So my talk is focusing on the main physics topics for EIC, and these physics topics were partially defined by a study that was done last year by the National Academy of Science, which provided a charge for the EIC to the Department of Energy. And the National Academy of Science decided that EIC can uniquely address 3 really profound questions about nucleons, neutrons and protons, and how they are assembled to form the nuclei of atoms. The first question is, how does the mass of the nucleon arise? The second question is, how does the spin of the nucleon arise? And the third question is, what are the emergent properties of dense systems of gluons? So I will be going through these topics, and will essentially highlight different aspects of the EIC science program now. And the first topic that I'll talk about is the origin of the proton mass, or how does the proton mass emerge from QCD, and why is the proton so heavy? So as we all know, protons are made up out of up quarks and down quarks. 99% of the mass of the visible universe is built out of protons and neutrons. They are really fundamental building blocks of matter. They are the only stable bound states of the QCD Lagrangian that we're aware of. However, the 3 valence quarks that are needed to define the quantum numbers for the proton only really contribute to 1% of its mass. So where does the nuclear mass really come from? Well, really, it's an emergent phenomenon. This has been known for decades. On the left, I show a figure with calculations from Dyson-Schwinger equations, as well as calculations from lattice QCD, where we show the effective constituent quark mass of the proton at different momentum scales. And essentially, what you see is that if you go to low momentum scales, you get the phenomenon of dynamic chiral symmetry breaking, which means that the constituent quarks start eating the gluon fields that surround them until they accumulate about 300 MeVs per constituent quark. And what is a very important feature of QCD is that this is even true in the chiral limit. So in the chiral limit, when the quarks are massless, we still accumulate about 300 MeV per constituent quark, meaning we get mass from nothing, or the Higgs mechanism is really largely irrelevant in the bulk of quote-unquote normal matter. So how can we try to then understand where this mass comes from? So why is the proton mass non-vanishing in the chiral limit? Well, one way to look at it is to relate the proton mass to the trace of the energy momentum tensor of QCD at 0 momentum transfer of the proton. It has been shown that at these low momentum transfers, heavy quarks contributions to this trace decouple from the low light quarks and can be absorbed inside of this beta tilde function you see on the left in front of the T-square function. And you really get 2 contributions only to this trace. You get a contribution that is due to the light quark mass, which is related to the sigma terms, and in the chiral limit is 0. And you get a term that is there due to the non-abelian nature of QCD itself, which is the trace anomaly term. This trace anomaly term is dominant because in the chiral limit, it's the only term that survives, and that's really still responsible for the proton being very heavy. You can see this term as sort of signifying that the proton mass is really the result of the vacuum polarization induced by the presence of the proton itself. I also need to highlight here that you can make the exact same expansion for the pion, but of course pion is the Goldstone boson of dynamic chiral symmetry breaking and has to be massless in the chiral limit. So unlike for protons, the trace anomaly must vanish for pions in the chiral limit, which is very interesting. The trace anomaly is clearly intimately related to dynamic chiral symmetry breaking and really to the emergence of scale in QCD itself. And that makes it such a fascinating quantity to study. So how can we access this? Really, this is a field that is still somewhat in its infancy. One of the key channels that we're looking for is upsilon production in the threshold region. And why is this? Well, the upsilon is it's a very small object. It doesn't have any quarks really in common with proton. Therefore, really, it's an optimal probe to probe the glue in the proton. The trace anomaly itself is a twist 4 operator, meaning that it's very heavily suppressed in high energy scattering. So you need to go to low energy scattering, which is effectively the production in the threshold region. On the right, I show a projection for this quasi-real upsilon production at an electron ion collider. Here we can, I included both electron and muon channels in this projection, and you can see that we can measure this fully exclusive in our hermetic detectors, and we can get very nice T-dependencies all the way down to the threshold region, meaning this is possible to do. We can start to constrain the trace anomaly through this process. We'll also get some related physics. We can, for example, start looking for beautiful pentaquarks, which I don't think would be easy to study at any other facility. And we will have sensitivity down to cross-sections of the order of 10 to the minus 3 nanobarns. Another way to study the origin of mass is really by studying the QCD energy momentum tensor itself, which gives access to all sorts of information on the matter structure of the proton. We can study this in the framework of gravitational form factors, which really describe the interaction of the proton with gravitons. Of course, graviton scattering itself is not really a feasible experiment. But if you take the process of deeply virtual quantum scattering, which I show here on the left, sort of with a rotated diagram of how we usually show it, in deeply virtual quantum scattering, we have a virtual photon that is emitted from the lepton, scatters off a parton inside of the proton, and in the final state emits a real photon. This process has if you take the two photons together, has the same quantum numbers as the graviton scattering, and has been shown to be sensitive to these gravitational form factors. And so very preliminary results have been published in the last years about these type of studies. The components of the energy momentum tensor that we can access this way are related to the mass and energy distribution of the proton, the angular momentum distribution, as well as the force and pressure distributions within the proton. Okay, the next big branch of topics is related to nucleon tomography. So, the central question from the NAS report is, how does the nucleon spin emerge out of a quark in gluon dynamics? And our very ambitious end goal is to try to map out the quantum mechanical structure of the proton really in 5 dimensions. So for understanding the nucleon spin, for decades in nuclear physics, we've been designing and conducting experiments to try to understand the nucleon spin puzzle, which is, which parts of the protonic structure of the nucleon really carry this nucleon spin, and why do we get this emergent phenomenon of a fixed proton spin of a half? So on the figure on the right, you can see a recent state-of-the-art analysis of the quark polarization and gluon polarization as we know them right now. And as you can see, there is an enormous region of uncertainty there. And really, by having the electron-ion collider and being able to get this massive information of the polarized DIS cross-section over this big swath of the phase space, we're able to shrink this uncertainty and really nail down how big is the contribution from gluon polarization exactly, how much is the contribution by the quark polarization. And then through different measurements, we will be able to constrain the contributions by the orbital quark and gluon angular momentum. Beyond just polarized DIS, we can study the transverse momentum structure as well as various spin-orbit correlations within of quarks within a proton through the process of semi-inclusive deep inelastic scattering, which is where we measure a single produced hadron in coincidence with the scattered electron. I just show some projected results because there's many of these transverse momentum distributions. In the top left, you see the a projected image for the up quark and down quark transverse momentum distribution in a proton that's polarized in the y direction. And in the bottom left, you see the quark transverse momentum in different slices of X for the Sivers function, which is one of the transverse momentum distribution functions. We don't just access the transverse momentum distribution, we can also study the transverse spatial position and the related concept of angular momentum through the framework of generalized parton distributions. The processes that we mainly study here are deeply virtual quantum scattering, which I already talked about in the context of the gravitational form factors, as well as various exclusive scalar and vector meson production channels. The EIC here is uniquely sensitive to gluons, C-quarks, and valence quarks at the same time. So we can really, by changing the center of mass energy, scan an enormous region in the phase space with the same experiments, which is very powerful. The figures I show on the left, in the top left, you see the projected precision on the transverse gluon distribution extracted from exclusive J-psi production. And in the bottom, I show the transverse distribution for C-quarks inside of, in the left, an unpolarized and the right polarized proton. And just to show how much more we will learn at the EIC, you can see here the collected data points in deeply virtual quantum scattering. At EIC, we really will fill out this entire phase space, and we'll have access to a wealth of information on GPDs that we can't access right now. And it will be a very nice connection with Jefferson Lab right now, where they measure the valence region, connecting this with deep into the C region. Sort of the holy grail of this tomography exercise is to try to get to the Wigner distribution. So you see here, there's a big diagram of different entities that we can try to measure at the electron-ion collider. But really, the Wigner distributions are fascinating because they encode the full quantum structure of the proton in quote-unquote 5 dimensions, meaning in longitudinal momentum fraction, in intact parameter space, as well as in transverse momentum space. This is a very challenging inverse problem that we are working on right now. And the challenge here is to reconstruct these full 5-dimensional objects from the observed exclusive, semi-inclusive channels, as well as jet production channels that were uniquely sensitive to these Wigner distributions in a different way. So beyond imaging, we have the topics before mostly focused on nucleon structure, but what can we really learn? What is really unique that we can do with scattering of electrons on nuclei. Here, really, the flagship topic is, of course, saturation. And here the question is the high energy low X limit governed by a universal dense saturated gluon matter? And then the next question, what is the nature of this universal dense gluon matter? So maybe a little bit more information. So if we take the proton structure at very low momentum fraction X, we have some problems with the typical linear evolution. So if you take the typical BFKL evolution, you get single gluon emission that really diverges as 1 over X, meaning that you get an increasing amount of splittings, which, you know, going to lower and lower X, you will get an increasing amount of gluons that split off, which will lead to the gluon distribution becoming infinite. And that's a problem because that really violates the Black disk limit in quantum mechanics. So we know, of course, that this can be true, and this has to saturate at some point. And one way to understand this is by by saying, well, of course we have splitting, but we also have recombination, and at some point we will reach some kind of equilibrium regime where the proton is really saturated with gluons, and we will split off as many nucleons as that we will recombine to get into this new phase. And there are different nonlinear models that describe this. This equilibrium point between splitting and recombination really defines a new scale, which is called the saturation scale. And this is a fascinating region to study because really the color fields in this, what we call color glass condensates, are extremely strong, but at the same time, we are in a perturbative regime. So we haven't been able to study something where we have this extremely strong color fields while still being perturbative. So why is EIC interesting for this? Well, really, for this, this is because of what they call the nuclear oomph factor. That is the fact that you get a very strong nuclear enhancement in the saturation scale. And really, the saturation scale for electron scattering of gold is as large as electron scattering of the proton at a 200 times smaller value of X, meaning we really are able to do an experiment that is equivalent to a much higher energy experiment in an EP collider. The other advantage of EIC is, of course, that we have the very clean initial state and exact control and exact knowledge of what our probe state was. So saturation is, very fundamental quantity of the nucleon and the nucleus. So it's going to show up in a lot of channels. And I will really here focus on the golden channels for this process, which are the diffractive processes. Diffractive processes can be described as interaction of a color dipole with the nucleus, and it's the only class of events that is sensitive to the spatial distribution of gluons. The cross-section depends quadratically on the gluon momentum distribution. At Hera, 15% of the EIS events were diffractive. And in EA, we can both study coherent and incoherent diffractive scattering channels, and we have this nice exclusive hermetic detectors where we measure really the full final state. So key observables for saturation, well, one of the key observables is the ratio of the diffractive to the total cross-section. As you can see from the projection on the right, especially in the right bottom where we have the ratio between the diffractive and the total cross-section compared between nucleus and between the proton, you can see that we expect a very significant enhancement in this ratio in the case of saturation versus no saturation. Also in diffractive scattering, we can study exclusive diffractive vector meson production. Here it is interesting to compare both the J-psi and the phi. Both predominantly interact with the gluons. And the phi is a significantly larger color dipole than the J-psi. So we are expecting to see these nonlinear effects that, as you can see on the projection on the right, will move the diffractive minima for this production process. And it will do this in such a way that it impacts the phi production significantly more than J-psi production. Finally, I want to say a couple of words about confinement itself and the process of hadronization. One of the questions that wasn't necessarily highlighted by the NAS report, but is definitely one of the cornerstones for EIC science is how do quarks and gluons interact within a nuclear medium, and what are the space-time dynamics for hadronization? So hadronization we can study in EA collisions, where we really have can use the nucleus as a laboratory to study this process. And we can do this by really going from low energy production, where in low energy production, the hadron formation happens within the nuclear medium, and then transition to very high energy scattering events, which we can both do at EIC, because in these very high energy scattering events, we can then move this hadronization process outside of the nuclear medium. And we can start to study how these different components interact with each other. We can also study topics such as momentum broadening, color transparency, etc. There's really a very large range of topics. Here is an example result about what we can learn about hadronization happening inside or outside of the nucleus. These are some projections for D0 meson and pi0 meson production. As you can see, this is really the result of 1 year of running at an EIC that's not fully operational yet at its full luminosity, and even with that, we'll be able to learn a lot about the process of hadronization. Finally, I'd like to, I brought up early on the EIC is a high luminosity polarized collider. The luminosity here is really driven by the topics of mass, tomography, and tomography, including transverse momentum imaging and transverse spatial imaging. The reason for that is that these processes are differential, typically in five quantities, and to properly measure these cross sections, you need to measure the 5-time differential cross section for all of these, and that requires a very high luminosity. Then the energy reach really is determined at the low end by trying to study the internal landscape of nuclei, something I didn't really talk about in this presentation, and at the high edge by QCD at extreme densities and saturation signs. The EIC users group is very active right now. There is a lot of new developments coming out of this in preparation for this new collider. Currently, the users group, as of last month, has over 1,000 members from 230 different institutions involving 31 countries in 6 world regions. And you can see here a world map of where the EIC users group is located. So it's really a big global effort, and for nuclear physics, it's a larger endeavor than we've ever partaken in. So to summarize, here are the main pillars of the EIC scientific program. We have the emergence of mass in QCD. How does the proton mass emerge from QCD? Why is the proton so heavy? What sets the scale in QCD itself? We can also study the mechanical structure of the proton. And then we will study the origin of the nucleon spin and, in extension, do 3-dimensional and even 5-dimensional tomography of the nucleon and the nucleus. We will study physics with high energy nuclear beams to try to study the properties of the color glass condensate and really understand where and how saturation sets in. And then we have a plethora of other topics that I only briefly mentioned or didn't even mention in my talk. For example, passage of color charge through cold QCD matter, jet physics in EP and EA, which is really a very quickly developing topic at this point. As well as, of course, physics beyond the stator model that we're sensitive to at EIC, and many other topics. Thank you.
So thank you very much for this exhaustive overview. There is a question. Marek, please.
Yes. Can you show your transparency number 20 again, please?
There you go.
No, sorry, the one with the decomposition of the nucleon spin.
The nucleon spin. This one?
Yes. So I have a comment that we have a rare situation today where lattice predictions for delta G and delta sigma have significantly smaller errors than the experimental errors. Very often lattice is able to reproduce things which are already measured, but right now they're quite precise predictions from lattice QCD for both the gluon polarization and the total helicity carried by quarks. So it's an important opportunity to test predictions of lattice QCD also.
Yeah, I completely agree. And this is actually an enormous milestone for lattice QCD. And this is really the scenario that we've always wanted to go to. There is some similar, possibility in the topic of the origin of the proton mass, for example, where we can really test some lattice predictions of things that have never been measured before.
Yeah. Okay, thank you.
Okay, so thank you a lot again, Sylvester, and to all the speakers of this.
You're very welcome.
So this session block now, since we are already 5 minutes late, I would suggest actually 15 minutes late. We do not do any break. We just now test quickly the speaker of the next session, and then we start over immediately. So is Peirong Lee ready to share, and Oton, Alexander, Thomas Husek, and Lely? Can you guys, one after the other, show your first slides to see that everything is working? Maybe Peirong Lee is the first to show, because the first 3 speakers have been tested, so we are missing the rest. Peirong Lee, please. Can you hear me? Okay, Oton, are you there?
Test my slides.
Yes, just thank you very much. Then we can test. Great.
So you should see them.
Perfect. Okay, perfect. So
okay, I will stop the sharing.
Yeah, sure. What about Peirong? Can you hear me? Can you also try to share your first slides so that we know that these all work? So no answer. What about Thomas Husek?
Yes, I'm here. Can you hear me?
Yeah, very well, Thomas.
Okay, let me try to share the slides. Can you see them?
Yes, perfect.
Perfect. Okay, thanks.
Then Lely. Very good. So can you also try full screen? Perfect. Thank you very much, Lely. Okay. So then the last person then missing is Alexander Arkomenko.
Yeah, I'm here. Yes, I shall try.
Ah, yeah.
Yes, wait a minute. Yeah, is it working?
No, we don't see.
Okay.
But we can also share your slides if you want.
Yeah.
Okay, then maybe we do like that. So then I would hand over the chair to Sharka, and then Slava can maybe...
Yeah, wait, maybe we should check Peirong Lee.
No, it was done already, Sharka.
It was done already? Oh, sorry.
Yeah,
okay, I didn't pay attention.
He didn't speak, but Lee was... Peirong was not there. No, you are right. Peirong Lee was not done, but he... Hello, so he didn't answer, so to me.
Do we have Perong online?
Yeah, he's online. I also wrote to him, but he's not answering.
Да, вот это он у тебя внизу, ткни мне вот это, да?
Okay, we have Alexander trying to share.
Yes.
Yes.
Yeah,
Okay.
try. Okay, but.
Okay, I've muted him now for a moment so that we can. Okay, so Pierong is missing, unfortunately.
Okay, so just wait 2 minutes for Alexander and Peirong maybe, and then we start, okay?
Yeah. Alexander said that.
Еще. Похоже, такое ощущение, что выключился, да? Нет, вот он был. И где он? Ну, ты по машине здесь.
So, Alexander, we hear you well.
Слушай, что ты? Может, туда перейдешь, на тот комп? Старый, Дима, может, здесь? Нет, нет, это не то. Нет, ты сейчас выйдешь вообще из машины.
Well, maybe the host may share the slides if it's possible.
Yeah.
Yeah, we can do that. Alexandra, can you hear me? I think we will share for you if. Okay.
На тот комп пересядь, там запускай. I shall change. Там просто не моей фамилии не будет.
Well, okay, we will mute him because he's.
Yeah. Okay. So, Peirong, would you like to, if you hear me, would you like to test your sharing?
Maybe he's not connected yet.
Oh, I see him on the list of participants.
Yeah, no, but maybe he has. Yeah, he's connected, but he left the.
Okay. Okay. Okay, let's start. I think we don't have much time. So, Slava, if you. Yeah. Okay. So we start the second part of our today programs oriented towards the spectroscopy, and our first speaker is Vyacheslav Matyunin from LHCb, who will be talking about studies of B hadrons. And please go ahead. We see your slides.
Hello, everyone. I'm going to tell about studies of B hadrons at LHCb. So first, I'll briefly cover the LHCb detector, then I move to the recent results about observation of new excited B baryons and measurement of B sub C meson production fraction and asymmetry. So the details on LHCb were given in talk by Martina Pili yesterday, but I just would like to highlight that LHCb is a forward spectrometer which is designed to study of B physics. And unlike B factories experiments, it has access to all of the species of B hadrons, such as lambda B baryons, Xi B baryons, and also their excited states. One of the main advantage of LHCb is good vertexing performance, which is used for the detached vertex method, which is used in most of the analysis of B hadrons in LHCb. So we reconstruct a primary vertex of proton-proton collision, secondary vertex of B hadron decay, and require the good separation between these two vertices allows to significantly suppress the background. So the first topic is about observation of excited omega B minus states. Back in 2017, the LHCb experiment reported about observation of 5 new omega C0 states, which are shown on this plot on the top right. And theoretical models describing these states also predict analogous excited omega B minus a state decaying to Xi B 0K minus. Using the full run1 plus run2 data sample of LHCb is performed the search for these excited states. The full decay chain of reconstruction is shown here, and the mass spectrum of intermediate daughter particles are shown on these two plots. The events in the peak region are kept for the further analysis, and after applying all the selection cuts, we obtain this mass spectrum and perform the simultaneous fit to wrong sign and right sign spectrum with common background shape. And in right sign, there are 4 peaks seen with significance noted here on the picture. The mass and upper limit on the width are measured and shown on the bottom. So as for possible interpretations, this state could be either angular or radial excitation of omega b minus, but and also it could be a higher mass excited omega b minus state decaying to yet not observed xi b prime 0 and k minus with missing pi 0. So the next topic is about excited lambda b baryons. Actually, there is a number of excited lambda b baryon states predicted. Here are some of them listed on the top right. So until recent times, only 2 excited lambda b baryon states were known. They are reported by LHCb in 2012. And the behavior of the state was confirmed by CDF. Well, today I'm going to cover, these 2 states were found in low mass region. And today I'm going to cover these 2 analyses, focusing on intermediate mass region and high mass region of the same spectrum. These 2 analyses follow the similar strategy. The reconstruction of excited lambda b is done in lambda b pi plus pi minus mass spectrum, where lambda b is reconstructed via either 2-body or 3-body decays. The corresponding mass spectrum are shown here. After applying all the cuts, we first look in low mass region. Here we can clearly see the 2 peaks, which were already shown with the lower statistics in 2012. And here we perform the simultaneous fit to all these 6 distributions. On top, there are distribution for right sign spectrum, and middle and bottom for 2 wrong sign spectrums. So this now we have much more statistics. Therefore, the mass is measured with higher precision, and also we give an upper limit on the width of this state. So now we can move to the high mass region, and here one can clearly see some peaking structure at mass about 7.15 GeV. Well, this peak is above xi b pi mass threshold. Therefore, the data sample is investigated in 3 non-overlapping regions corresponding to sigma b star, and non-resonant processes. So the simultaneous fit for these 3 regions is performed, and it is found that 2-peak hypothesis for this peaking structure is favored with respect to 1-peak hypothesis at the level of more than 7 standard deviation. So we report the mass and width of these states. And as for interpretation, this could be either a lambda b 1d0 doublet, but also interpretation as an excited sigma b0 cannot be excluded. So now we can move to the intermediate mass region, and here one can see the broad peak in both cases, on the left and on the right, and in case of different decay reconstruction method of lambda b's, and with significant, both are very significant, and by means of simultaneous feed of these 6 distributions, we obtain the mass and width of this new state. It is consistent with broad access recently seen by CMS, and mass and width are in agreement with being a lambda b to S0 state. Well, this peak is actually also above the sigma b by mass threshold, but the same trick is hard to perform as was done in the high mass region because the kinematic region of these resonances overlap. So here we just obtain the mass spectrum for lambda b pi plus minus for the signal component, and the final result is shown here on the bottom right. And as one can see, there is an indication of small fraction of decays through sigma b and sigma b star, and the dominant contribution is from non-resonant process. So the last topic is about measurement of B sub C minus meson production fraction and asymmetry. We continue to test the QCD by measurement of production fraction ratio of B sub C with respect to B0 and B minus mesons. For the analysis, the 2 data samples are used at, with 7 TeV and 13 TeV of proton-proton collision energy. The reconstruction is performed via these semi-leptonic decays. So the mass spectrum are shown on the top pictures, and yeah, they are for the signal B sub C meson case. And in the middle, you can see the production fraction shown as a function of transverse momentum of B hadron and the eta, the rapidity of the B hadron. So, and these pictures are for 7 TeV data sample, and on the bottom you can see the ratio of these distributions between 13 TeV and 7 TeV. So all in all, the rate does not change with energy, but shows some transverse momentum dependence. The production fraction is measured for in whole kinematic region and shown here. And also the B sub C minus B sub C plus production asymmetry is measured and found to be in agreement with 0. So this brings me to the conclusion. The LHCb experiment provides a significant contribution to the knowledge of B hadron spectroscopy. I told you about observation of new excited omega B minus states, about observation of 3 new lambda B excited states, and also about measurement of B sub C meson production fraction and asymmetry in proton-proton collision. So please stay tuned. We are looking for new results.
Thank you, Slava. Very nice result, very rich collection. Actually, you are very fast, so we have plenty of time for questions. And there is a question from Marek.
Slava, you mentioned at some point that the excited lambda B could also be excited sigma B0. Yes?
Yes.
Now, what are the prospects of resolving this issue by looking for the charge partners of such a sigma B? If it's a sigma B, then there must be a sigma B plus and sigma B minus approximately at the same mass. So what are the prospects of resolving this in LHCb experimentally?
And with what decays do you we can find it?
Well, you just rotate. You just rotate an isospin rotation, and if you have a state which you have a candidate for lambda b0 or sigma b0, there will be an analogous decay of, if it's a sigma b0, there will be an analogous decay of sigma b plus and sigma b minus going into the charm sector. So they would go to sigma b plus, say, and some sigma c and a pion.
Well, okay, I see. Thank you for the idea. I think we could have a look at it.
It would be interesting because you could resolve this, hopefully. I know that LHCb has a difficulty with neutral pions, but maybe you can find some mode which doesn't involve neutral pions.
Yeah, well, if there is a pi zero, then I wouldn't expect a
very
good separation here. But yeah,
okay,
if there is a decay chain without pi zero, yeah, we can have a look at it. Thank you.
Thanks.
Are there other questions? If not, thank you again. Very nice talk. Now, next speaker is Fergus Wilson from Babar. We'll be talking about measurement of absolute branching ratios of BDK in 2K in Charmonia.
Okay, can you see and hear me?
Yes, everything is perfect.
Okay,
please go ahead.
Let's just get rid of this. Okay, so I would like to give a presentation about the measurements of the absolute branching fraction with a K of a B plus to a state with a K on and an X state, which is a state containing a CC bar system or a Charmonium or Charmonium-like decay. And this is based on data taken on by the Babar collaboration. What's happening? So so in recent years, a number of Charmonium or Charmonium-like states have been measured, and QCD allows for complex structures beyond the standard meson and baryons that we're familiar with in standard model. However, some of these more exotic-like states have qualities that don't match into the meson and baryon spectroscopy that you might expect from standard model predictions. Either their masses are different or their decay products do not correspond to those expected for undiscovered non-exotic states. So for states with a charm or beauty bottom quark, these are generically called X, Y, or Z particles, depending on what is known about their quantum number. And on the right, you can see the spectroscopy from a recent report and review that's just come out. And so I will be talking about the X3872, which you can see is right in the middle here. And under the PDG nomenclature, it's known as the Chi C1 3872. The states you can see underlined with a blue line are confirmed states, whereas the ones which have dashed blue lines are just claimed and not firmly confirmed yet. So the X3872 state has been measured by a number of experiments over the years, first by Bell in 2003, and then in 2020 there's been a recent report, paper by LHCb, and you can see the progress that's been made. So some of the things we do know about this state is that Bell in 2018 had put an upper limit on the branching fraction of B to Kx of 2.6 times 10 to the minus 4. And recently, LHCb have published the width of the X3872 to be about 1 MeV. And this is considerably narrower than other XYZ states, which are more in the range of 40 to 180 MeV. And this narrowness makes the X3872 an excellent candidate for a missing mass analysis. So there are a number of interpretations of these exotic states. They could be tetraquarks or pentaquarks or H-dibaryons, which are quark pairs or anti-quark pairs formed, collected together. Or there are states such as molecules where there are bound states of what you might call the classical hadrons, loosely bound, held together. We can come up with ideas involving, without any quarks, just involving gluons, so-called glue balls. And then you can sort of combine these ideas into hybrids, where you have both quarks and gluons. For the X3872, there are a number of explanations, but I'm concentrating on a couple of predictions. So the molecular theory with a D0 and a D star 0 bar bound together predicts the branching fraction for X3872 to J psi pi plus pi minus around 10%, whereas the simple tetraquark model gives a branching fraction that's closer to 50%. And I've given you links to some reviews that can go into these in more details. So experimentally, what we have measured in the past is two-body B meson decays of the form B going to Kx and the X decaying to a particular final state. So we've measured the product of B going to Kx and X going to a final state, but we have not measured the individual branching fractions. So if we can do that, it'll give us extra information on the X3872. So down the bottom, I've shown you the Farman diagram for this decay. And the XCC bar can be a large number of charmonium or charmonium-like states, such as J psi, chi's, etas, phi's, and in addition, these exotic states like X3872. So the bar detector collected data between 1999 and 2008. It was an asymmetric E plus E minus collider. The data sample consists of 424 inverse femtobarns collected at the epsilon 4s resonance. And this is significant because the epsilon 4s decays almost 100% to B plus B minus or B0, B0 bar. So we can use that fact and the fact that we know what the initial energies are, the initial state, to do what is called a hadronic tag analysis. So we know that the final state is going to be a B and a B bar. So we reconstruct one of these Bs, so-called B tag, decaying to final states which are separated into states S and Y. So S are the D star and D0 and the J psi particles, and the Y part are the combinations of pions and kaons, both charged and neutral. So each of these are reconstructed exclusively. So there are often, many thousands of states decay channels that are reconstructed, but not all of these are useful. So a purity cut is placed on each of these decays, of demanding that they are going to be more than about 8%. But even so, that still ends up with about 300 different individual decay channels that are selected. So once we have the tag, we then look for a kaon in the opposite side of the system. And because we have the tag, we know what the momentum of the other, the form momentum of the other B is. And therefore, since we have the kaon, everything else can be assigned to the X state. So with that, we then boost to the signal side to the center of mass system. And as it's essentially a two-body system with the kaon recoiling against the X, we just have to plot the kaon momentum. And that is then related directly to the X momentum. the X resonances appear as peaks in the kaon momentum, and therefore we can just fit this distribution of both the standard model and the exotic charmonium-like states, and we can determine the absolute branching fraction, B to K X, directly, since we don't need to know the decay of the X to a final state. And then we use the already known product of B to KX, X to F from other measurements to determine the branching fraction of B to X of the X going to J psi pi plus pi minus. So the big change here over the 2006 analysis is that we have double the data, and we've also got 3 times increase in the signal reconstruction efficiency. And that is mainly done by keeping all the B tag candidates in an event rather than just one. So essentially we have 6 times the statistics. This doesn't necessarily mean a 6 times improvement in purity. So we use 2 neural nets to reduce the background, one targeting continuum production where E plus E minus goes to light quarks, and the second to target secondary kaons coming from the X decay side, which could mimic the primary kaon. This reduces the background significantly. But still a lot of it, we do a 5th order Chebyshev polynomial fit to the background by interpolating between regions where we expect there to be no resonances. We then apply a bin maximum likelihood fit to the background subtracted kaon distribution, and we use 9 resonances in that fit. We take the widths from Monte Carlo, including detector effects, and the positions from the PDG. So on the right, you can see the data before the subtraction of the background. Background fit is given in red, and you can already see where the various resonances are appearing. So on page 10, on the left, I show you the background subtracted data, and the red line shows you the results of the fits to the various resonances. The blue line represents the fit where we set the yield of the X3872 to 0, and that gives us the significance of the result. Now on the right, you can see the yields, and then those yields converted into branching fractions for the sort of standard model mesons. All those numbers agree with results that were published by Bell earlier. And then for the X3872, we take the yields from the J psi and the X3872 and their reconstruction efficiencies and the branching fraction of the J psi to its final states. We can then form a ratio, and from that we can calculate that the branching fraction of B to K X is 2.1 plus or minus 0.6 times 0.3 times 10 to the minus 4. And then we take the PDG for the product branching fraction, and from that we get the branching fraction of the X3872 to J psi pi plus pi minus of 4.1 plus or minus 1.3%. So in summary, these results have just recently been published. This is the first absolute measurement of the branching fraction of B plus to K X3872. It's the first determination of the X3872 decay to J psi pi plus pi minus. And if you take that to a branching fraction of 4%, it means that the simple tetracart model is ruled out at quite a high level, because it predicts a branching fraction of near 50%. And it's more favorable to molecular models, which predict a branching fraction nearer 10%. However, the pure models, molecular models, have other problems, so they are probably not the complete answer. And so this maybe attention should be placed on hybrid molecular models. We can now combine the branching fraction with measured width from, say, from LHCb to extract partial widths for the first time. And the method can in the future be applied to other decays of the X to other final states. Thank you.
Thank you, Fergus. An important result, thank you. We have question. I saw question from, I think, yeah, Mark. Yeah. Go ahead. Ah, no, it's Roberto. question from Roberto, please.
Yes, thank you very much for your talk. I have a few questions though. Concerning your result, essentially, I see, if you go back to the slide where you see the peak of the X3872, I see that on the right of the peak, there are a bunch of other high points that, of course, are not due to the X3872. And I was wondering if you are considering the fact that many other charmonium states have been discovered at 3823, 3840, that may explain those the peak. The other question is, I see that all the points below 1.1 are 0. So do you assume that the branching ratio of B to CC bar K is 0 below this chaos momentum? Because that's kind of a strange assumption, because I expect there also there will be a plethora of broad states to be considered.
I think the answer, well, for the actual peak, yes. I mean, there are predictions. For instance, there's a prediction for the 3876, but we just don't have the resolution with the data set we have to separate or in other states to really. With our resolution, we can't really make any determination of other states in that area. And I think, as you say, below 1.1, the data is consistent with 0, but the fit is allowed to progress below 1.1. I mean, it's just that the data has no real... so that width is actually taken from Monte Carlo, but the actual data has no real, because there is almost no data, it has no real input into the overall likelihood of the fit.
No, but you have points below 1.1 in chaos momentum, right?
Yeah, but they're all, after the subtraction, they're all pretty much consistent with 0.
I see.
So I think most of those points are probably 0 at some level.
There is one more question from Marek. Please go ahead.
Yes, just a comment. Can you show your summary transparency? Regarding the simple tetraquark model, in the simple tetraquark model, the X3872 includes CC bar and UU bar. Now, it is quite clear that QCD doesn't care about the flavor, if it's a U or a D. So in the simple tetraquark model, you automatically expect charge partners, because instead of CC bar, UU bar, you could have CC bar UD bar or CC bar U bar D. And as far as we know, no such thing exists. And these things have been looked for and nobody saw them. Another problem for the simple tetraquark picture is that it's incomprehensible. Why would a simple tetraquark just happen to be exactly at the threshold of D bar D star? This is totally not clear. So I think it's very hard to think about this state as a simple tetraquark. On the other hand, there is, I think most people who have worked on the problem think that it's some kind of mixture of a molecular state and the P-wave charmonium.
Yes, those are all very important points, yes. And I think the data is starting to also go in that direction as well.
Okay, thank you. I think, unfortunately, we have to move on. Thank you very much, Fergus. And our next speaker is Raul Rabadan from LHCb, who will be talking on excited charge meson spectroscopy from BDKs.
Hey, can you hear me?
Yeah, we can hear you.
Can you see the slides?
Yeah, perfect.
Right, so now I will go full screen and I'll start. It's okay, you can see them?
Yeah.
All right. So hi everyone, I will be giving an update on excited charm meson spectroscopy from BDKs at LHCb. Here is the outline of the talk. I'll start with an overview of the DJ spectroscopy and the experimental techniques for the study of excited charm mesons, to then focus on some of the latest LHCb results from amplitude analysis. So charm meson spectroscopy provides powerful test of quark model predictions in the standard model. There is a recent calculation of charm meson mass spectrum provided by Godfrey et al. That allows to make quark model spectroscopy assignments for the recently discovered excited charm states. The experimental status of the DJ spectroscopy is summarized in the plot on the left, and above the two ground 1s states, two of the 1p orbital excitations are well established. These are the D1-2420 and the D*2-2460, with the other members of this 1p multiplet being the broad D0-2300 and the D1-2430. There several new states have been recently discovered in the D pi and D star pi mass spectrums, and among them are the D2550, 2600, 2740, and 2750, which as labeled by PDG, and which were firstly observed in inclusive reactions by both Babar and LHCb. Quantum numbers from the 2750 state has been measured, but however, no definite assignment for the other resonance have been made yet. There are two different approaches for the searches of excited charm mesons. Inclusive reactions from production offers large statistics with poor signal to background ratio, and it's not possible to perform a spin analysis for two-body decays, and in the case of three-body decays, it can only distinguish between natural and unnatural spin parity. On the other hand, from amplitude analysis of multi-body BDKs, first, the data samples statistic is limited, but the backgrounds are usually low and well understood, and important is that a full spin parity analysis can be performed. This analysis can be complicated due to the presence of multiple interfering contributions, and amplitude analysis, it's a powerful technique to study complex decay dynamics by fitting the amplitude as a function of a phase space. Three-body decays can be described by two kinematic variables, and if in the case of having initial or final stage which are not scalar, additional angular variables need to be considered in order to fully describe the decay. So the fits can be done model dependently, or using more, typically following the isobar approach, or using more complicated models based on unitarity, and also from using quasi-model independent approaches in which some partial waves are described as complex beams. So the first analysis, the first decay that I want to talk about is from B minus to D plus pi minus pi minus. An amplitude analysis was performed to study the excited states in the D plus pi minus channel. And this was based on 3 inverse femtobars collected during round 1. A total of 20,000 events after full selection were available to perform the amplitude analysis. The data was fitted using a model consisting of 4 resonances. We were parameterized using relativistic Breit-Wigner line shapes plus 2 virtual resonances and a quasi-model independent description of the S wave. So due to the presence of identical pions in the final states, the 2 d pi masses are ordered by Bailey, and the Dalit plots can be seen on the plot on the right. The results from this analysis constituted the first observation of the D32760 and the D23000, and the mass parameters for these states and the other states constituting contributing to the model were extracted from the fit. And plots on the right show the projection of the d pi of the d pi masses projection and the results from the nominal fit. And complete results from the amplitude analysis are provided in the backups. The next analysis that I would like to talk about is the amplitude analysis of B minus to D star plus pi minus pi minus. This an amplitude analysis was performed to investigate the resonance production in the D star pi system, which gives access to both natural and unnatural spin parity states. And this analysis was based on 4.7 inverse femtobars collected during round 1 and in 2016 at 13 TVs. A high purity sample of 80,000 events was obtained after the full selection, and you can see the invariant mass, the invariant mass distribution, the plot on the right. And this time, in this decay, due to the presence of a vector particle in the final state, 2 additional angular variables are needed to describe the decay. Therefore, a 4-dimensional amplitude analysis was performed to describe the pi spectrum. Next slide, which is here. Yeah. So the data was fitted using different models. The first strategy was to fit the data with a model in which the contributing resonance were parameterized in terms of Bright-Wigner functions. Second, a quasi-model independent approach was used to describe the 1 plus S and the 0 minus amplitude, and this was the fit that gives the best description of the data. But additionally, a model in which the mixing between the mixing between the 1 plus amplitude is allowed was used to fit the data. So for the quasi-model independent approach, the process starts with a fit to the broad to the 1ps amplitude, in which the D star pi minus mass spectrum is divided into 31 non-uniform beams, and the Bright-Wigner term is replaced with 31 complex parameters, which are the magnitude and phase, which are free to float in the fit, while all the other amplitudes entering the model are described by relativistic Bright-Wigner. The list of amplitudes which are entering this model are given on the right, and the plots shown here are for the fitted magnitudes and phases of the 1 plus S magnitude. The process continues with a fit for the 0 minus amplitude, in which the previously obtained 1 plus S quasi-model independent amplitude is fixed, and the rest of the amplitudes are described by relativistic Bright-Wigners. Shown here are the fitted magnitude and phases for this 0 minus amplitude. And once these are obtained, the process continues by fixing both the 0 minus and the 1 plus S amplitudes and leaving free the rest of the Bright-Wigner parameters until the fit converges. So the plots here, the plots on the left show the results from the nominal from the nominal fit. The projections are for the d pi mass spectrum are shown, and the dominance of the D2420 D wave is noted, but also important contribution from the 1S quasi-model independent, and the D22460 can be seen. From this nominal model, the resonance parameters and the quantum numbers are determined, except for the D2550 and the D2430, which the mass parameters were obtained parameterizing these resonances with relativistic Bright-Wigner models. The table here shows the mass parameters obtained from the nominal model and the quantum numbers that were determined. As here again, the complete results of the amplitude fit, which includes the branching fractions, are given in the backups. Finally, the data was fitted using a model which allows for the mixing of the 1+ states. In this fit, the D1 prime and the D1 amplitudes are a superposition of the pure S and D wave amplitudes, and omega denotes the mixing angle. In this fit, D1 + S amplitude is described by a relativistic Breit-Wigner function, and only the 0- amplitude is described quasi-model independently. Yes, again, here from the table, you can see the results, I mean, the mass parameters obtained from this mixing model, and again, the complete results from the amplitude analysis, which are the fit fractions, are given in the backups. So, what about this charm-strange meson spectroscopy? Here, I'm just putting a reminder of the DSJ spectroscopy studies from LHCb in 2014. When an amplitude analysis of the BS to the 0K - pi plus decay was performed using a full round 1 dataset. From this analysis, the DS2860 state was resolved as an admixture of spin 1 and spin 3 components, and the mass parameter for these states were also determined. So besides this DS2860, there has been recently new states discovered in the decay and the star K mass spectrum. And the figure, the plot on the left summarizes the current experimental status of the DSJ spectroscopy. And same as for the DJ spectroscopy, there's a recent calculation on charm-strange meson mass spectrum, which provides important input to understand, to describe the recently discovered charm-strange mesons, and to look for new excited states. At LHCb, there is a work in progress on DS meson spectroscopy from amplitude analysis of B and BS decays. In summary, the resonance parameters and quantum numbers for several recently discovered DJ states have been determined for the first time from amplitude analysis of B- to the plus pi minus decays, and from B- to the star pi minus decays. And from this, the last decays, the mixing between the D12420 and the D12430 was studied, and the mixing parameters have been measured. There are more ongoing analysis on charm and charm-strange spectroscopy from B decays at LHCb, so there will be more interesting results coming soon. That's it. Thanks for your attention.
Thank you. Beautiful physics. We are looking forward to next results. There is one question from Marek. Marek, please.
Sorry, that was a mistake. I forgot to lower my hand.
Ah, okay. So please lower your hand, and we have time for a short question. Well, if not, everything was clear. There's a lot of information in your talk. Thanks a lot for the talk and for all the work. And we will move to the next speaker, this Peirong Lee, talking from BESS3, talking about the recent results on XYZ states.
Yeah, is it clear?
Yeah. Maybe full screen. Yeah.
Yes, can do this.
Very well. Go ahead.
Yeah. Okay. Hello, everyone. This actual report and the result of BESS3. Yeah, firstly, I'd like to introduce the BESS3 data samples for XYZ studies. BESS3 can directly generate the Y state by utilizing minus annihilation. Actually, the GP number is 1 minus as this decay generated from virtual gamma. So we can study the X states and this states by relative decay or hadronic transition from Y states. So battery has already accumulated around 20 inverse phase bar plus minus creation data events from 3.8 to 4.7 GeV. So in this year, battery take data about 4.6 GeV, which give us a opportunity to study the Y4660 in the detail study. Yeah. So in the experimental side, what we can do is to search for more activated states, study their properties, and also to find new decay modes. And also we can try to look for the transition between different states. So first, I'd like to introduce some Y states from battery in the recent few years. So first is about Y4220 and Y4220 and Y4360. So yeah, the mass and weights of Y4220 is measured in different channels, pi GSI, pi HC, pi prime, also omega K0. They all shows the mass is around 4220 and Y weight is around 60 MeV. So this resonance is observed in different channels, and the structure is consistent or close between different final states. But the nature of this Y4220 is not clear presently. So what we can do is to search for more modes. So first, I'll introduce the open charm decay channels, then pi BB star. Yeah, the cross-section measurement at battery could be used to study the Y states. So this is the most precision cross-section measurement. Yeah, use the data from 4.05 to 4.6 GeV. So we fit the cross-section line shape with a coherent sum of 3 body phase term and 2 Braithwaite functions. The statistic significance of the 2 readiness assumption or 1 readiness assumption is greater than 10 sigma. So we reported the readiness parameters of this 4220, which is consistent with the previous Hadron charm decay mode. So another one is the cross-section measurement of E plus minus to D1 2420 D minus and D1 2240 to D plus pi plus pi minus. So last year we reported a result with a fully reconstructed method, and this year we published we released a new updated result with the partial reconstruction method to improve the sensitivity. So we already use all the data sets between 4.36 GeV to 4.6 GeV. So we can see from the cross-section line shape distribution, we can see there are some indication of enhanced the cross-section for both processes between 4.36 and 4.42. So this may be indicated that this is the 4360 and the Y4415. Yeah, so besides, we also measure the cross-section of E plus minus 52 pi setup prime. Yeah. So another decay channel is Hadron charm final space, that means E plus minus 52 eta GSI. So this paper is just accepted by the PID. So we use the data from central mice 3.81 to 4.6 GeV. So for the left lowest line structure, we assume it is from the psi 4040, and we fixed the readiness parameter during the phase, and we try to extract the Y states, the two higher Y states. So we find the parameters or readiness parameters of this here. So this is the first time we observed the decay of Y4220 and Y4360 decay to eta GSI kind of space. So we list a table here to compare the readiness parameters between different channels. We can see the Y4220 mass and weight is close. But for the higher side, we cannot distinguish. So another cross-section measurement is E plus matters with data prime GSI. So we use the data from 4.178 to 4.6 dB. So this dependence of cross-section on the central mass energy should enhance around 4.2 GeV here. So this shape is this shape of cross-section could not be fully explained with one single psi, either psi 4160 or psi 4260. We fixed the mass with 2 PDD value of these two assumptions. So a coherent sum of these two precise states could provide a reasonable description of the data. So we list the solution in the table. So these two precise states with higher significance, especially for 4160. So another is cross-section measurement of E plus matters equal to pi0 GSI. So we measured this cross-section use the data between 3.808 to 4.6 dB. So during this process, we confirmed the just like we reported you in the charged channel. So during the stage, we used the charged channel reported Y4320 parameters to improve the precision of the life, the 4220. Yeah, so we list here we list the mass and weight of 4220, which is consistent with the pathological minus GSI. Besides, we also make a cross-section ratio between neutral channel and the charged channel. So we can see the average ratio is 0.48, so which is consistent with the axis symmetry. So another scenario is this. So as we all know, in 2013, both Battery and Bio also clearly reported that we found a CC3900, which is regarded as a 4-quark candidate. Yeah, they reported the environmental mass, the mass weight, and also this states mass close. Its mass is close to DD star threshold, and also as the final state contains a GSI, so we can conclude that this contains at least 60 bar, and also it has electric charge, so it should be contains UD bar. So besides this, we also reported the cross section and also the relative cross-section ratio between 2-body and 3-body at 4.62 GeV. So Battery also tried to find some new decay channels of this C3900. Yeah, here we reported the new decay channel of rho eta C. So we studied the E plus E minus decay to pi rho eta C at 5 energy points between 4.26 and 2.3 and 4.6. So the eta C is reconstructed with this magnetic modes. And also this channel is quite sensitive to discriminating the molecular states and the pentaquark states. Yeah, when we calculated the branch fraction ratio between rho eta C and pi GSI channels. So yeah, so when we select check the invariant mass of rho eta C spectrum, we find one strong evidence of this decayed rho eta C, which with a statistical significance of 4.3 sigma. So in the theoretical side, the interpretation of pentaquark states and the molecular states gives different value of this ratio. Yeah, that means rho eta C over the pi GSI. So Battery give the result is 2.3, which is closer to the pentaquark model overall. And the molecular calculation is highly model dependent. But our result is inconsistent with the Hadron thermodynamic model. That this model expects the pi GSI is larger than rho eta c. So besides, we can see we didn't find some more highly excited DC 4020 decay to rho eta c. So another result is we might determine the spin parity of this neutron DC 3900. We use perform a partial wave analysis for pi 0 GSI final states to determine the JP number is 1 plus. Yeah, 1 plus is more than 9 sigma than other half states. So also using the partial wave analysis, we give the mass and weight of this neutron DC, which is consistent with the charged DC 3900. So besides this DC study, we can also get the cross section of two-body process. That means the E plus minus 2 pi 0 DC, yeah, and the DC between pi 0 GSI. So the cross section is extracted, yeah, using a similar method we introduced previously. So we can see we found a structure around 4.2 GeV, and this resonance parameter is comparable with the previous called Y4220. So this result indicates that there is a strong correlation between the Y states and the DC 3900. So another one is X3872 space. We find this relative transition of X3872 to gamma GSI, gamma subprime, with data between 4.178 and 4.278. So we find the evidence of X decay to gamma GSI, yeah, with 3.5 sigma, but we didn't find evidence signals for gamma subprime final space. So we set upper limit of this ratio that gamma subprime branch fraction over gamma GSI. So we set the upper limit is 0.59 at 90% confidence level. So our result is agree with the environment, but a little bit challenged with the HCB result and the Bagar result. So we can try to give some conclusion is that this X is not likely a conventional thermodynamic space, but rather a molecular space or the mixture of molecular and thermodynamic space. Besides all these gamma GSI channels, we also find the X can decay to DD star with a statistic significance of 7.4 sigma. But we didn't find any evidence for gamma DD final space. All these final space listed in the table is measured the branch fraction ratio relative to pi by GSI, reported here. For some process, we set some upper limits. So I'd like to give a summary. Battery made a lot of progress in studying the thermodynamic space, and the spin parity of CC 3900 is determined to be 1 plus. And we reported the new decay mode of X3972. And also battery already finished the data taking at about 4.6 GeV, and which will be the Y4660 will be detailed study for that. So more analysis results are slightly in progress. Thanks so much for your attention.
Thank you very much for this nice overview. We have time for one quick question, if there is any. I do not see any raised hand, so we will thank you again. And our next speaker is Alexander Parchomenko, who will be talking on about tetra quark interpretation and production mechanism of the Bell.
Okay. Did you hear me?
Yeah, perfect. We see your slides. You are all set.
You see my slides, yeah?
Yeah, perfect. Go ahead.
Yeah, but
This is from your side, yeah, slides?
Yeah, it's from the side from the host. So
I think this is from your side.
Okay, so thanks to host who is already sharing. So just please
okay.
indicate switch.
Can I switch on my own? Yeah.
Just indicate when you are switching slides. And
okay. Yes. Okay. Did you see?
Yeah, we see your slides and we hear you well. So
yeah. Yeah, it's okay.
Yeah, it's perfect.
Okay. Good afternoon, everybody. I am thankful to organizers which invited me to give this talk. I will discuss new resonances which was observed by Bell collaboration and which is called YB 10,750. This talk was done in collaboration with Ahmed Ali, Luciano Mayani, and Wei Wong. And I will present these results. Outline of my talk is as following. First, I will give some introduction, show experimental picture. Then it will be discussion of mixing between tetraquark and bottomonium. In the third part, I will discuss production cross-section of the LHC. And then I will continue with the pion invariant mass and angle distribution in the corresponding decay of such a state. And then I will... Are my slides changing? Did you see?
Yes, there is just a slight delay.
Okay.
Yeah.
Okay. This is a picture. This is a picture about bottomonium states, and it really shows that a lot of states exist. And you see also, in addition to the conventional bottomonium states, which is presented here by, for example, y minus minus, epsilon 1s, 2s, 3s, and 3s. And it's also interesting states which called the epsilon 5s and 6s. And in this region, in principle, there also was found this new state, which was called YB 10,750. And it is somehow below, and this state I will discuss in my talk. Exactly. This is the corresponding energy scan by Bell collaboration, which was done in 2019. And you see here several peaks in the decay of, in this case, in the decay to epsilon 1s pi plus pi minus, then epsilon 2s pi plus pi minus, and epsilon 3s pi plus pi minus. And one can see really three peaks. This one, the first one, it is this new peak, which was observed by Bell collaboration. And these other two peaks, this is exactly epsilon 10,860, and this is the last one, 11,020. And you see also in all these pictures, there is a clear third peak at the energy of interest. So in the second picture also one can see this peak. So this is the output of the analysis, and you see here the masses of these resonances, and the last one, it is this one. It is the mass of the newly observed resonance. It is also have the same width as the other two resonances, 10,660 and 11,020. So they're compatible to each other. And also here it is presented the product of corresponding decay widths in E plus E minus multiplied by total branching fraction. So these quantities has been measured by Bell collaboration, and they show that the global fit is around 5.2 sigma. So it is a good observation of the new peak. It is not the final story, because later on, people, China group, here you see the corresponding reference, they also analyze the hadronic cross-section in E plus E minus annihilation in the region around BB bar production, and so they also they saw here the corresponding dip, and they also interpret this dip as a somehow as a performance of a corresponding new resonance 10,750. So this is the results, and in their analysis they got 8 solutions, considering that there is a masses of these particles, then total decay widths, E plus E minus decay widths, and also phi, the angle in the Breit-Wigner term in the shape function. So they made this analysis, they got 8 solutions, you see here, and this is only the first one, and it's presented here by the red line, and you see that also it is in a good agreement with Bell and Babar predictions, not predictions, but results, and this fit will reproduce the corresponding experimental data, will feed them, and you see here
Excuse
that
me?
they found. Yeah.
Alexander, just tell us on which slide you are. I think we may be a little bit behind.
I think for fifth one.
Okay, thank you.
Okay, and then okay, this is experimental picture. Okay, and that is I think, yeah, and this is a possible interpretation just now. Conventional interpretation of this state is that, for example, this new state and also epsilon 10,680 is a mixture of epsilon 5s and epsilon 4d state. But we give a different interpretation, considering that these two states are a mixture of epsilon 5s and hidden bottom tetraquark. So for this mixture, in principle, is supported by the large NC approach of QCD, and so in this case, this coefficient, this coupling is proportional to NC in power minus 3/2, and it should be really sizable when NC equal to 0. So you see a corresponding diagram, which are usually written in this picture, and this mixing really can be, and we are discussing also this mixing, and then the consequences of this mixing to the corresponding physical observables, for example, as the LHC and E plus E minus colliders. Mixing mechanism. If you have tetraquark states which contain hidden bottom, and also they consist of D and U quark, they are flavored tetraquarks. In this case, it's possible to, either spin basis, to get two states which are presented here. This one, these two states. We ignore their mass difference because it should be small, because of smallness of U and D masses. And also, because the production of BB bar component is only considered, so YB should be the isospin 0 state. And moreover, we see that there is differences between newly observed state and also these previously observed epsilon states. And in the case of YB 10,750 and epsilon 10,630, it is only 133 MeV, which is much smaller than between the other two. So we can consider only the mixing between these two former states, and this is presented here. And we introduce only one angle which somehow describes this mixing. But in principle, we can generalize this picture to the other state. And what we get from existing experimental data, in principle, this electron positron decay widths can be related to each other. And from this analysis, we got that this angle theta is approximately 12 degrees, but it can be a little bit different, for example, 10 degrees or 15 degrees, but in any case, it is of order of 10 degrees. So it is not so small, and it's really support predictions from the large NC approach for QCD that this mixing can exist. And it is not so small as one can expect. Okay, Hadron production, cross-section at the LHC. The corresponding procedure was worked out previously in 2013 by Ali, Hambrick, and Wong, and they calculated the corresponding branch infraction, corresponding cross-section for P to epsilon, and then to other states, which is nothing else but epsilon and s pi plus pi minus, this one, in the case of this state, and also it was the other state, 11,020, also they consider. But in principle, the picture is the same and the approach also is the same. So in the case of the newly observed state, we decided to use previous data and to scale the corresponding cross-section from the region of epsilon 7,860 to the lower state. And this is our basic formula, which we used here. And what we need here also, we need to cross-section for production of epsilon 10,860. So this is what we did, what process we considered here. And I shall show the results. We used the corresponding cuts which are accepted by Atlas CMS. It is also in PT momentum, then in the rapidity. And here you can see in this table our results for corresponding Hadron production cross-section in picobar. So you see that this cross-section are not rather small. And in principle, one can expect, I think in this case, maybe around 1,000 event at Atlas and CMS at the present statistics, and one order of magnitude smaller, I think around 100 events at LHCb. So also with the present statistics. Also, we calculated real Young process, and you see that it really suppressed in comparison with Hadron production. But in this case, this process is more clear. That is why maybe it's more easy to experimentally observe the corresponding events from the real Young process. Okay. So what's about LHC? Just now I go to E plus E minus again. And in this case, also we derive the corresponding differential cross-section. This is our general expression, which we used for the analysis. It includes several amplitudes, which are presented here, and they correspond to the resonance contribution from F0, F0 500, F0 980, and also from tensor meson, F2 1217, which contribute. And also one should take into account the corresponding non-resonant continuum contribution, which are combining in these quantities. This is amplitudes. So we try to perform this analysis. The only problem is that at present, Bell did not present the corresponding spectrum, for example, in pi plus pi minus in this decay. In this decay, epsilon 1s pi plus pi minus. So it is rather difficult to estimate the corresponding non-resonant continuum amplitudes. And so we put them 0. And just now we only estimated the contribution from the resonances. And here it is our plot. Here it is the distribution in pi plus pi minus in the decay. This one E plus E minus, this cross-section which is considered here. And you see that in red it is a contribution from scalar mesons, and in black it is a contribution from tensor meson. So you see that it's really rather interesting shape, which in principle can be modified by the corresponding non-resonant continuum contributions. So it can change. And the second plot, it is about the angular distribution, where theta is the angle between the pi meson and I think YB momentum in the pi plus pi minus rest frame. So this is the angle which is here, and you see that it's more or less symmetric distribution in comparison with 0, yes. But in principle, again, if background will be taken into account, so it also can be changed, but one need to know this contribution. And it's really interesting to see if it is possible to experimentally reproduce such distributions in future experiments and with data, with more data, for example, by Bell collaboration. And we will see also, we will weight this data, and I think if this data will be undertaken experimentally, so it's possible to make a fit and determine parameters which enter in our models for describing such type of the process. I mean, YB go to epsilon1s, pi plus, pi minus, or 2s, and also 3s. Okay. The next slide is about the branching fraction. So you see that Bell collaboration have measured the product gamma E plus E minus times B, where B is a total branching fraction. So gamma E is also known. B is not the total, but it is a branching fraction of this decays. So I'm sorry. And in this case, really, it's possible to determine the corresponding branching fraction of the decaying of the newly observed state to epsilon and s pi plus pi minus, and you see that it is at the level of a few percent, and in principle it can be observable, and it can be determined, I think, with a new Bell data. So, and also we'd like to note that due to the dominant theta quark nature of YB, YB 10,750 and its quark content, that such a decay to B sub S star, B sub S, B sub S, B sub S star, B sub S, and B sub S star, B sub S star decay, they are not anticipated, also which in agreement with the Bell collaboration data. Okay, and I shall go to conclusions. We consider the tetraquark based interpretation of the Bell data of new structure YB 10,750, which was observed in the plus minus annihilation. We assume that this state and epsilon 10,860, they are the mixture of tetraquark and BB bar state. And also we discuss the importance of the BB bar component in this newly observed state for its Hadron production and for the Drell-Yan cross-section at the LHC. And also, as I told you, the crucial test of our model is in the distribution and DPO invariant mass and angular distributions. And I think some other suggestions, some other implications of our model can be discussed in the future, and I think we shall present our new results on this talk. Thank you.
Thank you, Alexander. Thank you for the predictions. We have time for just one quick comment or question. There is Marek, I think.
Yes. Sasha, can you hear me?
Yeah, I hear you.
Do I understand correctly that you also predict isovector states at about the same mass?
No, we are not discussing the isovector state.
But why aren't they, I mean, they exist, they don't exist, what about them?
I think it is difficult to say because we consider only E plus E minus annihilation.
No, I am not talking about experiment, I am asking, do they exist?
In principle, it should exist, but what is its mass is difficult to predict because in our case, this YB, it is a YB 7,850, it is a mixture of this either singlet and also BB bar state. And the next one, it can have a little bit different mass. So.
Yeah, but in principle, such object should be possible to observe in LHCb.
In principle, yes, I agree with you.
So that's a very interesting test of your model, I think.
Yeah, I think we should think about this. Thank you.
Thank you.
Okay, thank you, Alexander.
Thank you.
And we move on. Our next speaker is Ottonu Vázquez-Doce from Alice. We'll be talking about measurements of baryon interactions and constraints on lattice QCD potentials. Yeah, we see the slides.
Okay, perfect.
Very well.
So,
go ahead.
Should I start?
Please.
Thank you very much. So my name is Otón Vázquez Doce. I speak for the ALICE collaboration. I will present you the measurements on proton-ion, proton-omega interactions and the constraints on lattice QCD. And basically, this will be a trip from high energy physics data through correlation studies to hadron physics and hopefully to the future of hadron physics. The part of the high energy physics data comes obviously from the LHC. There we study small collision systems, proton-proton and proton-lead collisions. And here the word small is actually meaningful for us. These collision systems create a source of emitting particles, what we call a source of emitting particles. That the sizes of the source that so determines the distances of the distance which the particles are produced are really small, around 1 Fermi. And this is actually very important for these correlation studies, this smallness of the source. Another key ingredient is the use of the ALICE detector. In particular for the reconstruction of hyperons. We exploit the full central barrier for the reconstruction of weak decays of hyperons, lambdas, psis, and omegas, so that at the end we end up with good statistics for studying the correlations between proton-psi and proton-omega pairs. And this correlation data gives us information in a sector that is the baryon-baryon interactions with the strangeness content. In this sector of strangeness, in contrast to what we have in nucleon-nucleon interactions, actually, we now have first principle calculations that they should deliver predictions with small uncertainties. We have recent developments by lattice QCD at the physical point now in this sector. But also in contrast with the nucleon-nucleon interaction on, for instance, scattering data of nucleons, the constraints that the experiments have to the theory are not so precise as in other fields and are not precise as the predictions of the theory. So this is exactly what we want to deliver, and I think we deliver with these correlation studies with ALICE is precise data in the low momentum range that is not accessible with other approaches. Obviously, the difficulties of other approaches is that it's difficult to have hyperon beams, in particular for psi and omega. So we deliver this precise data that is able to constrain actually these lattice QCD calculations, and this gives us instant gratification, like knowledge on the appearance of hyperons in neutron stars, the question of a state of baryon strange matter, the possible existence of dibaryons with strange content, etc. So this is the goal. And this is how we do it. We do it with the correlation function. We study correlation function in function of the K star, that is the relative momentum of the pair of particles of interest. And this correlation function can be written theoretically in this very simple way, where we have two main terms. One is the source that I was speaking about, the source of emitting particles that we have to characterize. And the other part is the two particle wave functions, so where the interaction is. In our studies of proton-psi and proton-omega, for instance, we have local potential that theoreticians provide us, and we have this tool, that's the Schrödinger equation solver, so that we can arrive to the two particle wave function, and together with the parameterization of the source, we arrive to expectation for the correlation function, for the theoretical correlation function. The correlation function looks in a simplistic way like this. If the interaction is attractive, you expect the correlation function at low K star values to be above 1. If the interaction is repulsive, you expect the correlation function to be between 0 and 1. Then the strength of this correlation in the correlation function will depend on the strength of the interaction itself and also on the size of the source. That's why actually small sources will enhance this correlation and are important for these studies. Obviously, the other main ingredient is the experimental correlation function. How do we obtain it? We have basically a ratio of the distribution of relative momentum of what we call here N-same is pairs of particles produced in the same again. For instance, we have a proton and omega produced in the same again. This is the same, the N-same distribution divided by the mixed event distribution. That is, we pair particles that are produced in different collisions, in different events. So proton from one event, omega from one event, etc. So obviously here we are looking at the correlation since the mixed events are naturally not correlated. And there are some some corrections in order to be able to compare with the theory. So at the end, we have three main terms here, right? We have the experimental correlation function, and we have the experimental correlation function that we know, obviously, because we determine it experimentally, the source function that we also know, and I will go through it in the next slide, and the interaction that we know to infer things about, right? So let's go with the source. This will be much better explained in much more detail, sorry, explained by my colleague Andreas Mattis in this talk, and he will go basically through the findings in this paper that we recently uploaded to arXiv and submitted to PLB. Basically, the idea here is that for all baryon-baryon pairs, there is a common source. So that means that if we study via femtoscopic study of proton-proton correlations, from proton-proton correlations we have many more statistics than for other pairs, and we can study in detail the characteristics of the source and then use these characteristics to study the interaction of other pairs. This sounds rather simplistic, but it's actually very hard work. You will see it in Andreas' talk. We take into account several effects, like the effect of strong resonances for all hadrons, and in particular, collective effects. These collective effects, you see the influence here. Actually, this is the determination of the radius of the source here in the y-axis from proton-proton femtoscopic data in blue, in function of the transverse mass of the pair, and you see this nice dependency due to collective effects. So at the end, when we want to study proton psi and proton omega pairs, we just need to know the mean transverse mass values for these pairs, and automatically we go to this map of the source size, and we know the radius. You see that this radius, this is before the corrections due to resonances, are really, really small, at even lower than 1/3. So the radius is, the source is characterized, and now we need the data. The data, as I said, we take from proton-proton collisions and proton-lead collisions. Particularly in proton-proton collisions, we use the high multiplicity trigger of ALICE, and in high multiplicity events, we have an enhanced production of strange hadrons. This allows us to have nice statistics you see for proton psi pairs and from proton omega pairs, the numbers that you see here. And this is actually how ALICE reconstruct the hyperons. This is the example of the omega invariant mass through the decay into lambda and KO. So we take the source, we take the pairs, and we build the correlation function. This is the first correlation function that I want to show you. This is the proton psi correlation function from proton-lead collisions. It has been published in PLL, in this PLL paper, and this is actually the first observation of an attractive interaction between a proton and a psi baryon. This you see it from the point that the black points are the data. You see from the fact that the black points are above 1, as I said before. This means an attractive interaction. And they are not only above 1, but they are above the Coulomb expectation. This is the Coulomb expectation, so the correlation function that you expect for this radius, the radius here in proton-lead collision is a bit higher than the radius in proton-proton collisions, the radius of the source. So for this radius, you expect this correlation function if you take into account only Coulomb interaction. So there is obviously something more there because the correlation function experimental is more enhanced. So we plug in the strong interaction. We take this potential from lattice QCD, whole QCD collaboration, the proton psi minus potential in different isospin and spin combination, and we plug this into CATS, and so that with the source characteristics that we have, we end up with this prediction for that is the orange band with the Coulomb plus strong interaction for the proton psi correlation function. And we see that actually the lattice QCD does a good job in describing the data. And as I said before, we can go further, and this has implications. If we believe in lattice, we believe also that the single particle potential for psi is slightly repulsive in Newton-rich matter, 6 MeV. And this slight repulsive interaction has consequences on how these psi values appear in neutron stars or in Newton-rich matter, pushing them to appear at only higher densities. Also, it has consequences on the equation of state. This allows us a stiffer equation of states, and so also to reach higher masses in this radius to mass typical plot of equation of state. So this is for what respects to the proton-led data and the proton-psi correlation function. Now we move to proton omega. And basically we increase the level of strangeness. We are in the sector strangeness -3 with proton omega. This for lattice is actually is good news, because the higher the mass is, the more stable the calculations are. And the calculations, again, from the whole QCD collaborations, predict in this channel, proton omega, the presence of a strange divarium, the proton omega divarium, with this binding energy that you see here, 2.5 MeV of binding energy, if you consider a strong plus Coulomb interaction. And this also, and the shape of the potential predicted by the whole QCD collaboration, you can see here, the proton omega potential. These are recent calculations with physical quark masses, as you can see here. And the characteristic of this potential are rather extreme. You see that the attraction and the potential goes really deep. It's a high attraction, and when we compare it with the previous potential that I showed to you, the proton-psi potential, we see that at small distances, the level of attractiveness in proton omega should be much higher, and in general, the potential is much more attractive. So, if we believe in everything that I just said, we expect an experimental correlation function that is more enhanced in proton omega due to this extra level of attractiveness. So only data can say, and this is the data. This is the data in proton high multiplicity collisions at 13 TeV. It is reported in this paper that we submitted to arXiv and submitted to Nature. And these are the results, the proton-psi and the proton omega correlation functions, compared with several predictions. So first of all, we see we see a clear evidence of the attractiveness of both interaction. We see that they both exceed the Coulomb expectation. This we confirm already, we saw it already for proton-psi, but now we confirm with better data. And in particular for proton omega, we see that this correlation function is more enhanced with respect to the proton-psi correlation function. You see the values that we arrive at 3, in proton omega, we arrive at 6. And this precise data in proton omega allow us to compare it to lattice. This, if we look at this comparison with lattice, we see that now we have 2 curves for lattice, the orange and the blue. We have 2 curves because in this channel proton omega, there is an indetermination in the treatment of the inelastic channels. That is actually not there in the proton-psi. And also, we also see in this comparison of our data that we can go to this region of 150 MeV, and the expectations from lattice go below 1. This is an effect of the presence of the bound state. And with our data, this effect is not present. Of course, we can go deeper experimentally. We can search for the signal of this depletion, the signal of the bound state in different systems with slightly larger sources that will help to disentangle the systems or not of this bound state. We can also bring a bit of more light in order to distinguish between these 2 lines, giving experimental information of inelastic channels of studying lambda psi and sigma psi, but overall, the picture is that with this small radius and this precise data, we are already with our ALICE data matching the precision of the lattice QCD expectations. And this is basically everything that I wanted to show. I hope I have convinced you that the LHC provides precise testing of the hadron-hadron interactions at very small distances with data that substitutes other approaches or complements other approaches. That already first principle calculations with our data can be tested, and especially for interactions involving hyperons. And of course, please stay tuned, because round 3 and round 4 will be a big boost for these studies. We will do new combinations of new studies, of new correlations, go to differential analysis, and also investigate 3-body interactions. And that was all from my side. Thank you very much.
Thank you very much, Dr. for your talk. We have one question from Marek.
How realistic would it be to try to do such an analysis for charmed particles rather than strange? Because that would be really exciting for obvious reasons.
With round 2, it is not realistic. If you are speaking about, for instance, about sigma C, it it is very difficult, even with run 3, this reconstruction of sigma C could be very tricky, but we have already some analysis of values in this sense. So far with run 2, it is not possible. For sure.
Just to mention that this in principle could be a way to test the nature of the LHCb pentaquark. So really exciting. Okay, thank you.
Thank you.
I have one short question myself, if I may. Why did you consider to use Lorentz invariant parameters? Because the K star is not Lorentz invariant. This will complicate the comparison with other measurements in the future.
So far, all the analysis that we've done in general, this is, let's say, inherited from femtoscopic analysis, right? Looking for the size of the source. Here we change the paradigm and go to study interaction, but actually studying in K star is really easy to see visually, because it's not only that we compare with lattice expectation in K star, but for instance, when we did, actually, we reported also K-on proton analysis, etc., lambda proton analysis. There's a direct translation between K star and the momentum of the scattering of lambda proton, K-on proton, where you see opening of different channels, and you see these different bumps due to the opening of different channels. So it has a very really direct interpretation and comparison with the precision of scattering experiments.
Yeah, but it's not like stable comparing between experiments. It's just a suggestion, right?
Yeah. Thank you.
Okay, thank you. Thank you very much for the talk. I think we have to move on. Our next speaker is Tomáš Husek, who will be talking about radiative correction for the decay of sigma 0. We can hear you.
Yes, so you can hear me. I'm now sharing my screen. Can you see it?
Almost, yes. Full screen, maybe.
It should be full screen already, isn't it?
Okay, yeah, maybe, yeah.
I don't know.
Okay, go ahead.
Tell me. Okay, so first of all, I would like to thank the organizers for the opportunity to present my work. I would like to tell you something about radiative corrections for the decay of sigma baryon to lambda hyperon and electron-positron pair. And this work has been done in collaboration with Stefan Leupold from Uppsala University. So let me first motivate a bit my talk. So one of the major challenges in contemporary particle physics is to actually understand confinement. How are the building blocks like quarks distributed inside of composite objects, hadrons? So in a simple example of nucleons, we can perform electron-nucleon scattering and extract electromagnetic form factors, and then deduce some low energy quantities like magnetic moment, electric magnetic radii. But there are also other ways how to study composite objects. We can replace one of the building blocks by something else. So in the case of nucleons, we could take the down quark and replace it by the strange quark and study the resulting hyperons. And actually studying hyperons then can provide us with complementary information to what we already know about nucleons. But experiments involving hyperons are rather challenging because they are very unstable. So electron scattering with hyperons might be rather difficult. Anyways, we have some ways how to, for example, access electromagnetic form factors at high energies at electron-positron colliders, but only above anti-hyperon thresholds. But at low energies, it would be nice to actually take this feature of their instability of hyperons and try to find a decay of hyperon into other hyperon and electron-positron pair, which can be then studied in future facilities which are being built now. But the question is if there is such a Dulles decay in ground state baryon octet sector. And the answer is yes, there is this sigma to lambda plus E minus decay, which allows us to study form factors at very low energy at the energy window of 77 megaelectron volt, and actually provides us with information about electric and magnetic transition form factors. And it can actually allow us to extract transition radii, important hadronic information from the experiment. But this experiment needs to be very high precision with very high statistics, and actually there is additional obstruction that, based on theoretical predictions, these parameters, these hadronic parameters, these electric and magnetic radii are supposed to be very small, so they might compete with QED radiative corrections. So let me introduce our notation on the simple calculation of leading order, to calculate this process at the leading order. So for the sigma lambda gamma vertex, we use Dirac and Pauli form factors, and these can be further translated into magnetic and electric form factors and further expanded in terms of hadronic parameters like magnetic moment, magnetic and electric radii. Typically, electric radius is much smaller than the magnetic radius, so we can neglect it in our calculation, and then, for example, the result for the matrix element squared is given solely by the magnetic form factor. I'll be using kinematic variables which are defined here. Most importantly, let me stress that X is actually normalized electron-positron invariant mass. So the radiative corrections for this decay were studied already in literature in the 70s by Sidhu and Smith, but only in the soft photon approximation. So actually, they didn't cover well the low X region in their calculations. So their radiative corrections were negative all over the Dalitz plot, even though they already knew that the total radiative correction is positive. So what we do, we decided to reinvestigate these radiative corrections to calculate the Bremsstrahlung beyond the soft photon approximation, and also explicitly calculate the contributions which were considered in the literature to be negligible, just to check if this is the case. So just to give you some very brief introduction to the calculation. So for the Bremsstrahlung, we actually, our goal is to calculate radiative corrections for inclusive process. So in the end, we would like to integrate over the energy and emission angle of the Bremsstrahlung photon. So for this, we need to expand the form factors which appear in the Bremsstrahlung contribution in this way, which then allows us to perform this integration. Then considering these additional contributions, which actually contain other hadronic form factors and which are rather complicated. But the most important feature is probably that these diagrams are by power counting already UV divergent. So one really needs to introduce some hadronic form factors to tame the ultraviolet behavior. So for these two diagrams, for the one photon irreducible contribution, we can actually take into account just constant form factors, constant electric and magnetic form factors, which turn out into this form for Dirac and Pauli form factors. But for this diagram, for the correction to sigma 2 lambda gamma vertex, we actually need to take something a little bit less trivial. So we take form factors which are consistent, which have a high energy behavior consistent with Brodsky-Lepage limit. In any case, when the calculation is performed, one can find out that indeed this contribution is negligible, so one can safely neglect it in the analysis. So let's come to the results. So this is how the corrections to the Dalitz plot look like in terms of these two kinematic variables X and Y. It's given in percent, but it's not really illuminating. So this might be actually better to show you the corrections to the one-fold differential decay width. Here we can see the respective contribution from the virtual corrections, which is in red line, and the Bremsstrahlung correction, which is the green line, and their sum, the blue line, which is the total radiative corrections. So on the x-axis, you actually see this invariant mass of the electron-positron pair. And there is this low X region where we see that the radiative correction is actually positive, and this makes the fact that the overall radiative correction is also positive, which is the important feature we've been looking for with this beyond soft photon approximation treatment. And actually, if we calculate the next to leading order decay width over the whole Dalitz plot, we can predict that we can predict such a ratio for the it's a ratio of the branching ratios of the sigma to lambda e plus e minus decay and sigma to lambda gamma. And actually, one can see that in this ratio, the effect of the electric form factor is negligible. And since in this ratio also the magnetic moment cancels out, we are left with a single hadronic parameter, which is the magnetic form factor slope. And we can expand this ratio in terms of this hadronic parameter A. And then if we take into account as additional uncertainty the higher order corrections, which we of course didn't calculate. So if we take into account the uncertainty of basically stake only at the next leading order, we can predict the ratio R model independently with explicitly stating the contribution with this hadronic parameter. And we see that our result is consistent with what was given in the literature before. And actually, if we use the exactly same physical constants and restrict ourselves only to the contribution which were used in the past, we can actually see that the results are equal. So this also tells us something that our calculation is most probably correct. Other thing which one can do is to realize that branching ratios of all the decays of neutral sigma baryon is to sum to 1. So then based on the ratio R, one can actually translate this to respective branching ratio of these decay channels. So we can actually predict very precisely these branching ratios. And if we want to be very conservative, assuming 100% uncertainty on this parameter A, we can actually have model independent results for these branching ratios. And one thing I would like to say is that what might be actually the effect of the radiative corrections for the extractions of the magnetic form factor slope from the experiment. So actually, it can be shown that this is related to the half of the slope of the correction in the low X region, a little bit above the threshold. So it means like taking the slope somewhere here. So it's approximately minus 3.5%, this correction to the to this parameter A. And what is interesting that actually the prediction for the form factor slope is actually 2 times smaller. So this immediately shows you the importance of the radiative corrections. You're basically trying to measure something where the QED radiative corrections give you 2 times bigger contribution. So let me summarize. So we have calculated the complete inclusive next to leading order QED radiative corrections to the differential decay width. It means we've calculated corrections which relate the QED leading order calculation of sigma to lambda e plus e minus decay to experiment, which also allows arbitrary many photons in the final state. So in particular, we calculated the branch stratum beyond the subphone approximation. We explicitly calculated also the 2-photon exchange contribution and correction to sigma lambda gamma vertex. And we've shown that these corrections, which also include other hadronic form factors, can be safely neglected. So we were able to actually present our results in model-independent ways with only a single hadronic parameter A. So I showed you also some predictions for branch stratum of these branching ratios of these 2 processes, and in the end showed you that actually the correction to the form factor slope is rather big, and it's really important to use the radiative corrections in the experiment. And I will leave you with a view on Prague, and thank you for listening.
Thank you so much for these results and predictions. Other questions? I don't see any. Everything was clear.
Okay.
So I think since we are behind the time, we will move on. Thank you very much.
Thank you.
And the next speaker is Lely from BES 3. And you'll learn about the lambda C physics and prospects. Yeah, we have the slide. We don't hear you yet. Are you muted?
Okay, how about this?
Yeah,
hello.
that's much better.
Sorry, that's some problem. Okay, good night, good morning, or good afternoon, depends where you are. Thank you very much for inviting me to give this talk about so that I could introduce something about the lambda C studies at BEST3. So I would like to give a talk about lambda physics and prospects at BEST3 on behalf of the BEST3 collaboration. So the talk includes in 4 parts: introduction, measurements, prospects, and short summary. The quark model describes that lambda C is composed with a heavy tram quark and an unexcited semi-zero UD diquark. So based on this picture, the heavy quark effective theory predicts that lambda C may provide more powerful tests on internal dynamics than D and DS methods. Lambda C is the lattice tram baryon, and lots of the heavy tram baryons such as sigma C and also cascade C will eventually decay into the final states involving lambda C. Thus, measuring the decay property of the lambda C is important for study of the tram baryon spectroscopy. And besides, measuring the decay of the lambda in the study of flavor hadrons. However, before 2015, the status of the lambda C measurements is very poor compared with the tram methods. This slide shows some lambda C measurements in PTG 2015, and the total summed branch ratios of all of the decays are actually less than 60%, and more than 40% decays are undetected. And even for the measured branch ratios, the uncertainties, few of them have some precisions better than 10%, and quite a lot of them are measured with very poor precisions. And there is almost no absolute measurement, and almost all of the branch ratios are measured relative K-pi mode, and the lambda C decays to neutron will account for quite a large branch ratio in lambda C decays, but there is no such kind of measurement. So based on this kind of situation in 2014, BEST3 decided to collect data at 4.6 GeV minute at this point, just above the lambda C pair production threshold. So this shows a lambda C cross-section measured by Bell collaboration, and in 2004, the highest energy that we can achieve is 4.6. So we decided to take in data here. Based on this data sample, we did some works on the study of the lambda C decays. The BEST3 method, the branch ratio of the lambda C decays to lambda E plus U neutrino, and the lambda C goes to lambda mu plus mu neutrino. And this shows UMS distribution that we observed from the data. And we observed 180 signal events for the 2 decays, and measured the branch ratios to be 3.6% and 3.5%. We also test the lepton universality by comparing the ratios of the 2 decays. The mathematics, especially for this one, provided important test for different theoretical predictions, and also provide inputs for calibrating the lattice calculations. And BEST3 also measured the absolute branch ratios for 12 hadronic decays, PK short, PK pi, and so on here. This shows a beam constraint mass distributions that we obtained from the data, and we can see the measurement, the signal is very clear. And the second column shows the measured branch ratios compared with the values shown in PTE 2015. We can see quite a lot of measurements are significantly improved. For the PK-pi mode, BEST3 obtained smaller values than Bell collaboration, but in the future, more data will be used to confirm the measurement. And the absolute, the improved branch ratio for PK for PK mode is important for calibrating the other decays of the lambda C. A best rate also measured the branch ratios of the singly kappa suppressed decays of the p kappa and the PKK. We used the single tag method to obtain the branch ratios, and the measurement is relative to PK mode, and the ratios of these decays to PK mode is firstly obtained and then input the branch ratios of the PK method by best rate. So the branch ratios of these decays can be obtained. This kind of study can shed light on on some dynamic information of the lambda C decays, and also in the measurement, lambda C goes to P5 is of particular interest because the decay diagram. So this kind of measurement can provide an important test for the relevant theoretical models. And also, Basri observed the first decay to the final state involving the neutral lambda C goes to English short pi. The importance of the measurement is that the relative branch ratio of the neutron involved mode to proton involved mode can provide an essential test to the spin symmetry, and also can be used to extract the information of the final state interactions. From the data we obtained, 83 second event extract the branch ratio of the decay to be 1.8%. And by combining the branch ratios of the PK mode, we can obtain the two ratios here. Based on the two ratios, we between the amplitudes of the SS singlet and SS one to be here, based on this paper. Based on the data taken in 1 month, and the integrated luminosity 0.57 was fit by data. Basri has published 14 papers, and 1 paper was just submitted recently, and some other works are undergoing currently at Basri. This slide shows the lambda C measurement in PTE 2020. If you compare it with PTE 2015, you can see quite a lot improved measurement has been achieved in recent years. That's great news. In the first half year of 2020, Basri has collected about 4 inverse fair of data in the energy region from 4 roughly at these 5 ending points. About 20 math intervals for each ending point. The new data is about 7 times larger than the data collected in 2014, and about 74,000 lambda C pairs are produced in new data. Taking advantages of the data collected near the lambda C pair production threshold, so Basri will have the clean signal and low background in the measurement, and also will have well-controlled systematic uncertainties in the measurements. This will be very important in the future studies. And by using the new data, we can almost systematically study almost all of the lambda C decays. For example, in the absolute measurements of the branch ratios, form factors, and also the decay symmetry measurements. And we can also investigate channels containing the K-line and neutron by using the Damatine method. This will greatly enrich the decay of the lambda C particles. And in the next few slides, I will show some prospects of the lambda studies at Basri. So firstly, in the exclusive semi-diatonic decays, especially in the form factor extractions in these decays. Firstly, actually, the measurement has been performed by the Cleo collaboration in 1995 and 2005. This shows some plots from this paper, and they extract the ratio of the form factors based on the heavy quark effective theory, and confirmed that the F2 is non-zero with a 5 standard deviation. In 2017, just after the publications of the branch ratio measurement of these two papers, of these two channels, from the Basri, the lattice performed the first calculation of the decay rates and branch ratios and alpha vectors by using this series expression to give some information of the decays, and also lattice provided the first estimation of the CKM elements VCS based on the measured branch ratios from S-ray, and also it's predicted from factors. This is the first determination of the VCS by using the lambda system electronic decays. So in the next few years with more data, we can test all of that, all of the predictions from the lattice. And we can also search for some other semi-leptonic decays. For example, lambda C goes to lambda star E plus neutrino, and lambda C goes to neutron E plus neutrino. The predicted branch ratios of these decays is about 0.4%, something like this. And in the hadronic decay space rate, we systematically study the decays with double exchange diagrams because compared with the charm mesons, it is expected that double exchange mechanism will play an important role in the lambda C decays. And we know that there are several decays which can only decay. This kind of decays can only proceed with a double chain mechanism, but the branch ratios shown here is very, the uncertainty is actually very large. So with modulator, PI3 can precisely measure the branch ratios of these decays and can provide important data to understand this mechanism because these channels are clean and very straightforward to understand the physics. And we can also study the singly capable surprise decays such as lambda KP Pazar and so on. This kind of decay is important to understand the internal dynamics and the non-factor reservoir diagrams. This table just summarizes the expectations and also the measurements for two-body singly capable surprise decays, and we can see that some channels are missing and some channels measured with large uncertainties. So for example, for p-0, in 2017, we actually published a paper, but since the data is limited, we only report the upper limit at 90% confidence level. So with more data, we can study for other topics. In hadronic decays, we can also study the decay symmetry parameters in lambda C two-body decays. Currently, all of the measurements are concentrated on the studies of the lambda C equals to baron plus a series scalar, and there is no measurement in lambda C equals to baron plus a vector. So that's a good place for study this kind of decays. And we can also study performing the partial wave analysis in hadronic decays. And PI3 will have advantages in analyzing the final states involving the neutron and PI0. And we will also search for the exclusive decays containing the neutron pillar. As I mentioned, this kind of decays will account for quite a large branch ratios. Enrich the decay families, and also can provide some tests on acyl spin symmetry. And we can also explore some Kirchhoff symmetries in lambda C decays, but the data may be quite limited. And we can also search for some weak radiative decays, such as lambda C goes to gamma second plus, because the branch ratio is okay at T-4. So if currently the BPC clear energy can reach up to 4.9 GeV, but we cannot reach 5 GeV. So in the future, if the BPC can further increase its clear energy to 5 GeV, we have the access to study the sigma and the cascade C. This will be very interesting topic in the future, but it may be possible in the future. So quite a lot of the studies can be performed in the future if the energy calculation here. So short summary, PI3 in the last few years, PI3 has performed quite a lot of work in understanding the lambda C decays. And with more data in the next few years, PI3 will systematically study the decay property of the lambda C baron in some semi-leptonic studies, hadronic studies, also the weak radiative state decays. Thank you very much for your attention.
Thank you, Lei, for this very impressive amount of work. Do we have questions? Doesn't seem to be the case. So thank you again for this very nice overview.
Thank you.
And we are looking forward for for more. This is the end thanks to all speakers. This is the end of our second part of our program. Since we are running late, we will shorten the coffee break to 5 minutes for the audience. So we will come back like 28, 2 minutes to half. And for the speakers for the next session, please stay connected and we will test the connection. Okay, thank you.
Oh, maybe we start with Isabella. Are you there, Isabella?
I think
hello, I'm here.
Yeah.
Yeah, maybe you can share your slides to see whether it all works.
Yes, we can see.
Okay, can you put it in full screen?
Yes, I'm trying. Okay.
Yeah, perfect. Okay, Jan Hui. Jan Hui Zhu, are you there? I think he tried already before, actually, at the beginning of the second session.
Yeah, I already did that test.
Exactly, I remember you did it before, so it works perfectly. Then Martin Drahal.
Yes, I'm here.
Hello, Martin. Could you try to share?
So I will try to share. Okay.
Okay, perfect. Thank you.
Okay, so it also moves, so everything seems so.
Florian, Jonas.
Yes, hello. Should work as well. I will share the screen. Can you see the slides?
Yep, perfect.
Perfect.
Yep. Then David Muller.
Yes, I'm here.
So I see your screen.
Are we visible?
The screen, yes. The slides, not yet. Can you? No, but the slides. Okay, the slides were not visible. You were sharing the screen, right? Okay. Okay, David. Yes, perfect. Thank you. I see the slide. Thank you very much. Then, yeah. Then Sushanta.
Hi, can you hear me?
Yeah, very good.
Let me see the screen. So can you see it?
Yeah.
Okay. Thank you.
And then Hamza.
Yes, I'm here.
Yeah.
Should I press the screen share button? Yes.
Yes, just to try. Yes.
Mm-hmm. Can you see my screen?
Yeah. Can you try full presentation view? Full view.
And see my. Yes. Yes. It's okay.
Yeah. Perfect. Okay. Good. Then I would say that Isabella can share her slides again, and then we can start in 1 minute. So, Hamza, you need to stop sharing.
Yes, because I cannot share my screen.
Hamza, you need to stop sharing so that Isabella can share. Perfect. Yeah.
Okay.
Okay, so before starting, please try to keep your time because we are already 20 minutes late. And since the session takes anyway until 9 o'clock, we do not want to prolong too much. So the first speaker of this first block that will deal with meson productions and hadronization, Isabella Babiatz. And she will talk about production of eta sub C in a plus C minus and proton-proton collision. Isabella, you have 15 minutes in total, inclusive discussion. So for the talk, 12 minutes.
Okay, thank you for introducing me. And I will, my talk will be based on the two references. One from Gajs Wichr Goncalves, Roman Pasecznik, Paweł Schaff, and Antoni Szczurek. And let's start. My content is a short introduction and description of the main idea, the transition form factor, and some application of the model, and also the results for LHC, which is exact the LHCb experiment, and Babar data for the form factor. The main idea is to describe the eta C1s and the eta C2s, which is a bound state of the C and C bar quark, which is a pseudoscalar meson. And our proposition is to introduce the light front transition form factor, which is based on the light front quarkonium wave functions. And we obtain our non-relativistic quarkonium wave functions through the equation of Schrödinger equation from several potential models, which is Buchmann potential, Kollner, logarithmic oscillator, and power-like. We use the first time from Fock-States expansion, so it is a color singlet state. And we use also the derivative prescription, which is valid for weakly bound system. And we get our light from representation of the wave functions. The wave function for eta C is a little bit different from eta C2s. In eta C2s, we can see that the main part of our wave functions is in negative, and this is the example for Buchmann potential. But other potential gives more or less similar wave functions. This is a short description how we can relate our transition form factor for both on-shell photon with the decay width and going into the non-relativistic QCD limit. We can obtain also the relation with the radial wave function at the origin. And we get some results. We can see that our form factor for both on-shell photons get the best description for the power-like potential, which is potential linked with the MC mass of the quark, which is equal 1.3 GeV. And also we derived the R prime with other potential like chimeric logarithmic power like Buchmann time, and we can see the results. Also, we perform the results for eta C2s, and we can see that our agreement with experiment data are much better. What we have to also consider the uncertainty of the experiment. So this is still to be checked. And this is our normalized transition form factor. When we normalize the form factor for one virtual and one real photon to both on-shell photon, and we can compare our results from our model to Babar data from 2009. And we can easily see that a power-like potential gives the best descriptions, and we can say that probability is due to that this potential gives the best description with this mass of the quark. And also we show the prediction for the eta C2s. And our transition form factor is perfectly symmetric with exchange with the virtualities of the particles between exchange them, and this is for the Buchmelter potential, which is and other form factors for other potential looks similarly. And also we have predictions for the eta C2s. And for QC, we did the calculations for the form factor with others variables like omega, which is the difference divided by the sum of the virtualities, and also Q squared, which is average of these two squared virtualities. And we can see that easily that with omega there is no changes, but with the average Q squared is some changes with going to the high Q squared average. And the main results of our work is how to apply our form factor to other processes, because it is very nice to apply our form factor, which is for both virtual photons into KT factorization approach, and in our case it is we apply this to PP to eta C production, and our master formula for the for KT factorization is it is written here, where we can see this is a square of matrix element and also the unintegrated Green distributions functions, and our matrix element, which is for the first time presented by us, is here, and here is actually hidden our form factor, and the relation between our form factor and this function I is written here. So it is easy to connect our form factor for gamma star to eta C with this I function, which corresponds to our form factor for gluon-gluon fusion, two virtual gluon fusions. And we can also compare our results to NRQCD form factor, which looks like that, and we can see that this NRQCD form factor is in main part related to radial wave function at the origin. And this is explicitly also our matrix element with this function I. In order to have some control of the under our model, we normalize our form factor to radial to decay wave from the experiment, and we derived our form factor on the on-shell point from leading order formula, and also from the next to leading order formula, and we normalize our form factor to this value. And this is the main result. We perform calculations for different unintegrated gluon distributions functions, and we can see that our results are a little bit different at the low PT of the meson, and go to more or less similar results for the high PT of the meson. And this is also for the power law potential, which we say that it is one of the best, gives one of the best description. And we did the calculation for the Kayamar method made from MHT 2014 next leading order, and we use also Jung-Hauptmann set second, and also the Kayamar plus Kutak unintegrated gluon distribution functions. We can say that our model good describe the results, the experimental results for 7 TeV and 8 TeV, but we can guess that for the higher energy, maybe some other mechanisms should be included to good describe these data. For the curiosity, we also did some calculations like okay, so this is for the eta C2S predictions. We did the predictions in the LHCb regime, so it is the rapidity between 2 and 4.5. And we did also for the several unintegrated gluon distributions functions and with normalized form factor. This is for the 7 and 8 and 13 TeV. And we did also calculations with some other several form factors with one normalization at the on-shell point. So we can see that more at the beginning of the plot, we can see that these gives the same, more or less the same results. But with the high PT, there's a little bit difference between these 4 potentials. This is also for the eta C2S, and the square root of S is equal to 7 TeV. At the end, we did the calculation with our form factor, which is not normalized, and also with our form factor, which is normalized, and which is the most interesting, where we apply the point-like coupling, so we don't consider in the matrix element the virtualities of the gluon in our predictions. So we get this almost straight line. And the conclusions. I would like to say that maybe it will be most interesting to see also the form factor for the eta C2S in future experiments, maybe in the double tag mode, where to we present the application for the form factor in the KT factorization, which is the method where is the approach of when we can see the virtualities of the particles are included, and also our comparison of our model to LHCb data for 7, 8, and 13 TeV, which is the last point in summary, that we can see that the uncertainty of the choice of the unintegrated gluon distributions is higher than the choice of the potential model for form factor, which can be seen on the almost last slide. Thank you for your attention.
So thank you very much for these nice results. Are there questions or comments? Okay, it doesn't seem to be the case. I also don't have further questions because what you shown was very clear. So thank you again for this nice talk. And then we thanks Isabella, and then we move to the next talk directly by Yan Hui about hadronization study at the LHC with Alice.
Thank you.
Hello?
Yeah, you have just to enter full screen. It didn't work properly. Yep, now it goes. Perfect. So you also have totally 15 minutes, which means 12, 13 for the talks, okay? So
okay.
Okay, thanks. Good evening to everyone. I'm Jian Hui from the CCNU and the GSI on behalf of the ANIS. And today I will give a talk about the hadronization studies at the LHC with ANIS in heavy flavor sector. First is the motivation. As we all know, the heavy flavor methods production cross-section can be calculated using the factorization approach as a convolution of three factors: the parton distribution functions, the hard scattering cross-section at the partonic level, and the fragmentation functions of the heavy quarks into heavy flavor hadrons. Due to the lack of knowledge about the heavy quarks into bands, fragmentation function models cannot provide the predictions for the heavy baryon production. In this case, the heavy flavor baryon production measurements are essential to verify and develop hadronization model, especially for the using the charm baryon to meson ratio. In PP collisions, this ratio can be used to test the PQCD calculations. In proton-lead collisions, it helps to investigate the cold nuclear matter effect. In lead-lead collisions, we can study the modification of the hadronization in the QGP medium. For instance, the models, including coalescence, predict an enhancement at low and intermediate PD with respect to the string fragmentation model. Here is the structure of the ANIS detector and the mean sub detectors used for heavy flavor baryon measurement, including the ITS, TPC, and the TOF. These detectors are located in the middle rapidity smaller than 0.9. The ITS consists of 6 layers of silicon detectors and used for tracking, vertex reconstruction, particle identification, multiplicity determination. The TPC and the TOF are main detectors for the tracking and the particle identification. Here is the charm band. Analyze the charm band can be measured by hadronic decay channel in ANIS. For the lambda C, it decays to the pk pi, and also for the pk short. For the sigma C, as we know, it almost 100% decays to the lambda C and the pi. For the Xi C, Xi 0, it decays to Xi and pi. For Xi plus, it decays to the Xi and the pi. As usual, charm baryons can be fully reconstructed according to the environment mass distribution. You can see in the bottom plot strip examples of the fate of the environment mass distribution for the lambda C, sigma C, and the Xi 0. These distributions are obtained after the particle identification of the Doppler tracks and the topological selections. So after the single extraction, the yield are corrected by the acceptance times efficiency in order to get prompt cross-section. The feed down from the beauty decay has been subtracted. Here I show you the charm baryon measurement through the semi-leptonic decay. Since the neutrino cannot be detected, so the unfolding technique has been applied in order to convert the PD of E electron Xi pair into Xi 0. So in this case, the peak of the electron and the Xi is broader than the fully reconstruction. So we extract the single using the right sign minus the wrong sign. Then we use the detector response matrix to implement unfolding. After that, the efficiency corrections is also applied to obtain the final PT differential production cross-section. So from this slide, I start to discuss some interesting newest measurement in ALICE. Here is the lambda C to D0 ratio as a function of the PT with different multiplicity. So the purple points are with the high multiplicity, and the blue points are with no multiplicity. So you can see from no multiplicity to high multiplicity, we see the significant enhancement at low and the intermediate PT. The dashed lines are the model's predictions produced by the PCR8 with more large tune. It marginally underestimates data points. While the PCR8 with model 2, as you can see, this model is the color reconnection beyond the leading color approximation, which describe the data well. From the blue to the purple shadow area, we see the significant enhancement, which indicates that the color reconnection effect increased when the multiplicity increased. Here is the lambda C to D0 ratio as a function of the multiplicity in different collisions system and the different collision energies. So the full cross means the PP collisions, and the open circle is the P-LED, and the open diamond means the lead. So in low multiplicity region, we already see the enhancement in PP collisions with respect to the electron-positron collisions. And from low multiplicity to high multiplicity, we see the lambda C ratio increase smoothly. However, in high multiplicity region, we see the PP is consistent with lead. So does it means that the ratio is already saturated in high multiplicity in PP collisions? Here is the lambda C from the sigma C decay to D0 ratio as a function of the PT in PP collisions at certain TV. So we see the PCR8 with more large tune, as I show in the black line. It largely underestimates our measurement, while the PCR8 with the color reconnection beyond the leading color and the mean He and the rough models, both of them are consistent with each other, and they both of them can describe our data points. So the left plot is the fraction of lambda C from the sigma C decay. We can also see the same enhancement, which can indicate that the enhancement in lambda C to D0 ratio can be only partially explained by the sigma C fit down. Here are the sigma C to D0 ratio and the XC to D0 ratio as a function of the PT in PP at certain TV. So both of them are measured by the hadronic decay channel, and they are the first such kind of the measurement at LHC. Left plot is the sigma C to D0 ratio. So similar as lambda C to D0 ratio, PCR8 with more large tune underestimate our measurement, while the PCR8 with color reconnection beyond the leading color and rough models can describe data well. In the right plot is the XC0 to D0 ratio and the XC plus to D0 ratio. So for the measurement of the XC0 is down to the low PT 1 GV over C and has a final PT bin. the XIC0 and the XIC plus are compatible with each other. But however, up to now, they cannot be described by any model. In this case, our XIC measurement can provide additional constraint for hadronization model. Here is the ratio of the electron and the hadronic decay branching ratio. So this is also the first such kind of measurement in ANIS. The XIC0 electronic decay branching ratio has very large uncertainty, which caused the large uncertainty in the in this ratio. However, in ANIS, we fit the PT spectrum measured by electronic and hadronic decay separately. Then we make the ratio and propagate the uncertainties. So in the right plot, as you can observably see, our measurement has smaller uncertainty with respect to the PDG value, which can provide a better constraint for the decay branching ratio measurement. Then I go to the summary. We have found that the hadronization in PP collisions is quite different than electron-proton collisions, and it has a strong dependence on the multiplicity. So up to now, the PCR8 with color reconnection, beyond leading color approximation, and the statistic hadronization model can describe lambda C to D0 and sigma C to D0 ratio, but not for XIC to D0 ratio. We have first branching ratio measurement for XIC0 with ANIS, and it has smaller uncertainty with respect to the PDG value. We have many heavier charmed barrier measurement like sigma C, XIC, and they are very useful for the total charm cross-section. So that's all. Thanks for your attention.
Oh, thanks a lot. Super nice results. Impressive, this analysis. Are there any questions or comments? Okay, then I will ask you a question about, I think it was slides number 5 or in this ballpark when you show the neutrino cello. Here it is, right? I didn't understand completely how you can reconstruct the kinematic of a decay having the missing neutrino. So how do you then evaluate the purity, the resulting purity for the Xi0 sub C?
As you can see here, well, in the environments of the electron and the Xi, so first we subtract the background of the wrong sign. Yeah. And then we have the as you can see in the lower plot, this is the response, as you can see, the reconstructed PT electron Xi in the y-axis, and the x-axis is generated PT of the XIC0. So this detector response matrix is used to convert the electron Xi to XIC0. Yes. Yeah.
Now I have understood. Are there other comments or questions? Okay, if not, thanks a lot, Yanui, for these nice results. And we can move to the next speaker, who is Martin Zatrahal. And then we'll speak about the dispersive representation of Kaun and eta decays via 3 pions. Very good. So,
okay, so I hope you hear me. I hope.
For you, you have 15 minutes.
Okay, so good evening, good afternoon, good morning, and also good night, depending on the part of the globe you currently are. I will talk about our work with Karl Kampf, Mark Knecht, and Eugene Novotny, which was recently published in Physical Review D, on dispersive representation of Kaun and eta to 3 pi decays. During the last decades, the experimental knowledge of these decays has greatly improved. We have high statistic data for the charged K1, for the K-long decay, and also for the eta2 3pi decay. In all the relevant cases, also the cusp was observed, also analyzed. I have given here only some of the experiments. There are also other either already published or ongoing or even planned. So there is indeed a harvest of data. These processes live in the realm of the low energy QCD. So the appropriate methods are theoretical methods are chiral perturbation theory and lattice QCD, and those data are important for the studies of the QCD of this regime. The eta2 3pi is useful for the determination of the mu minus md quark masses, and the processes with the cusp effect can be used for the determination of pi-pi scattering lengths. Traditionally, for comparison of the data with the theories, one uses the direct spot parameterization, which introduces kinematic variables and then parameterize the square of the invariant amplitude in terms of the polynomial in those variables. However, unitarity tell us that the amplitudes can possess the non-analytic or non-analyticities. For example, this pion loop has a branching point at 4 and pi squared. It can happen that in the physical region this point doesn't appear. But for example, in the pion processes where the kinematic region is given by the neutral pion masses, and as they are lower than the charged pion masses, there could appear that the branch points at those 4 and pi charged squared will appear in the kinematic region, which leads to the cusp effect, and the polynomial parameterization will not describe well amplitudes which possess some those effects. One has to use some more complicated theory-inspired parameterizations. Nowadays, those are mainly those following from the non-relativistic effective field theory or some various dispersive approaches. So this is also our aim. What is the construction of a fully relativistic parameterization valid at the two-loop level in the low energy expansion that possess correctly all the analytic properties and takes into account the isospin breaking connected with the difference in the pion masses. The isospin breaking effects connected with the electromagnetic interactions, so Virchow photons and photon emissions are neglected in our description. For the construction of the parameterization, we use those four tools. The first one is the analyticity. This it enables us to construct the full amplitude from the knowledge of the discontinuities along its branch cuts. Another tool is the unitarity that enables a computation of imaginary part of some amplitude just from the knowledge of the amplitudes of intermediate processes. We need low energy expansion and some hierarchy of the partial waves that they are dominantly real, and that S and P waves prevail over the other partial waves. The last tool we extensively use is real analyticity. That tells you that the discontinuity that is needed in the dispersion relations is the imaginary part which is provided from the unitarity. So the typical reconstruction procedure for scattering process follows proceeds in these steps. We take the leading amplitudes as the inputs. The unitarity give us the imaginary part to the higher precision, and then dispersion relations gives us the full amplitude to the higher precision up to some polynomial. We can use this construction also for the pi-pi scattering processes, and this enables us to perform also the second step and obtain the amplitude to the two-loop level, having those coefficients of the polynomials as parameters. However, this procedure was illustrated for the scattering process. If we want to use it for decay process, two obstacles appears. The one is easily solved by analytic continuation in the kinematic variables into the decay region, but more problematic obstacle is with that if we have a decay process, the decaying particles unstable, so we have lost the real analyticity, and there is no connection between the imaginary part and the discontinuity. We can try to solve this by using analytic continuation in the mass of this decaying particle to the stable values. But the question is how to find the right analytic continuation that would lead to the physical amplitude. For that, we use tape that for our procedure, we need the right analytic properties only in the region where the low energy expansion works. So we can use the study of analytic properties of all possible diagrams that would appear in Feynman diagram method for obtaining the right analyticity properties, and this would guide us to obtain the right analytic continuation in this mass of the decaying particle. For such analysis for one-loop computation is simple because there appear mainly polynomials, but it is more complicated at two loops. For the isospin pion masses, it was discussed already in the 60s by Kacher and Pronzan. And if you want to include also the isospin breaking connected with the different masses, you have to. We had to perform it by ourselves. So fortunately, we were successful in extending this analysis also for that case for the processes, those two processes which have the cusp effect, and the remaining processes remain to be done. So in those three cases, we have succeeded in the construction of the parameterization. I am showing here the parameterization for eta to 3 pi 0 for different prime masses. And you see that the amplitude is parameterized using the polynomial part, which depends on 3 constants, and the unitarity part in which the correct analytic structure is hidden in 17 kinematic functions of this type that are multiplied by some polynomials that contains again the same parameters as the polynomial part, but also other parameters from the intermediate processes. So if you take those other parameters as known from some other analyses, the parameterization of the amplitude is given as using just 3 parameters, and they appear there just linearly. But I should note that if you want to use it for data fit, you need to fit the square of this amplitude, so those parameters appear there quadratically. So I have shown you that we, at least I have given you a hint that we have obtained a parameterization for k and eta to 3 pi decay amplitudes that possess the correct analytic properties at 2 loops. Important is that all the ingredients are in closed analytic form. The worst is that you have to compute some dispersive integrals, one parametric dispersive integrals. For the processes KL and eta to 3 neutral pions, this parameterization, those parameterizations include also the isospin breaking connected with the difference of the pion masses. And the extension to other processes is under progress. Important on this parameterization is that it has the connection with the perturbation theory can be easily restored, and so one can study effects on the result from perturbation theory on this result of final state scattering, which was illustrated in one of our previous paper. And nowadays we're preparing a fit of data for eta to 3 pi 0 with a cusp, and eta to pi plus pi minus pi 0 in the case when we take the pion masses same. And we are also planning to perform extension of this method. If we add 1 over NC expansion, we should be also able to parameterize this process, which is also popular nowadays. So I think that I have used my time well. So
Yeah.
this is everything I wanted to tell. So
okay, thank you very much, Martin. So for this nice talk about this theoretical development. Are there questions? Well, I have one. So you said that you are preparing to fit the data. My question was, your work, the work you presented here, how does this differentiate from, let's say, the studies of these calculations for the case as, for example, eta goes to 3 pi 0, which is, let's say, the novelty aspect of the work you presented?
Okay, so there should be, as I have tried to illustrate, less model dependency as it was in those previous studies, and I think that there should be also something like a simple. The analysis should be simpler because it is indeed that you have a table of values of those schematic functions, and you don't need to perform some numerical computations or such things.
Okay, so parameter space is reduced and then model dependence is reduced. So this would be, it will be easier to analyze, I mean, to use this formalism as a reference for analysis.
Yeah. And also there is something like a more direct connection to the tulip calibrate division theory, because still there should be some explanation of the differences, whether it is connected just with the final state scattering, if it is connected with the low energy constants. Or,
I see. Okay, thank you very much. Then thanks, Martin, again. Then we move to the next talk by Florian Jonas. He will now talk about omega and eta prime production in proton-proton collision at VLHC, measure with ALICE. I would like to encourage the audience not to give up, despite of the fact that it's already past 8, and to participate with the comments and questions, because it's important for our speaker. But anyway, I am awake, and please, Florian, go ahead.
Yeah, thanks to everyone for sticking around. So I will be talking about omega and eta prime production in proton-proton collisions at the LHC, measured with ALICE. And I wanted to begin with a motivation. Why would we be interested in measuring these heavier neutral mesons? And the first point, a little bit from a theoretical point of view, that measuring hadron production in general allows us to test theory calculations, as we saw in previous talks already, but also to constrain the things going into them, such as parton distribution functions and fragmentation functions. And these sorts of comparisons we have done with a variety of particles in the past, for example, pi zeros and etas. But here really the omega and the eta prime are very interesting complementary probe due to their heavier mass and the spin in the case of the omega. I also wanted to point attention to one thing here, and that is that the availability of data can spark interest from the theory side for future theoretical analyses. So to make this point, I put a quote here from a paper dealing with vector meson fragmentation. No such considerable interest has been shown towards vector meson production due to the scarcity of the data available so far. And yeah, we are looking forward to filling this scarcity of data. But of course, there are also motivations from a more experimental point of view. The first one, a little bit an indirect one, that our signal is background in other measurements. And I put two examples here. First of all, direct photon measurements, which are an important probe for the quark gluon plasma. In these measurements, they have a very large decay photon background. And here, for example, the omega contributes as the third biggest source to decay photons. And also we contribute here with the omega, for example, to dilepton measurements that we're doing with ALICE. And here better knowledge of the background leads to smaller uncertainties on the signal. And the more direct motivation is that hadron production in general is a very nice probe for the quark gluon plasma. For example, one can study the suppression of the production of these hadrons in p-lead and lead-lead collisions due to the presence of the QGP, for example, which is not expected in the PP baseline. And this has also been done for several particles. And here again, the omega and the eta prime are an interesting complementary probe. And they sort of give us a little handle on the dependence of QGP transport properties on things like mass, spin, or flavor. But we can also look at modification of the meson properties themselves, such as mass and width, due to partial restoration of chiral symmetry in the QGP. So now that I hopefully convinced you that this measurement is interesting, I tried to boil down the analysis on one slide. So what you can see on the top is the most probable decay of the omega meson, 2 pi plus pi minus pi 0, and at the bottom of the eta prime, 2 pi plus pi minus eta, where then the pi 0 and the eta furthermore decay to 2 photons. So the idea here is to measure the photons with ALICE, then reconstruct the pi 0 or the eta via the invariant mass, then measure the charged pions with ALICE's tracking capabilities, and then again via the invariant mass using these three particles, then end up with the omega and the eta prime. So how do we actually measure photons with ALICE? We have several ways of doing so. First of all, our two main calorimeters, the EM-cal and the FOSS. And the MCAL is a lead scintillator sampling calorimeter. It is the smaller, larger of the two, so it has larger acceptance than the FOSS. However, it has a lower resolution where the size of one readout tower is approximately 2 times the Mollier radius. The FOSS, on the other hand, which is located here, is based on a lead tungstate scintillation crystal technology. It has a smaller acceptance, however, the higher resolution where the crystal size is about 1 time the Mollier radius. Since 2015, ALICE also has a new addition to our existing calorimeters, the DCAL, which is simply an extension of the MCAL at the opposite side in azimuth. So here, but it's not shown in this schematics. A completely different approach to measuring photons is the so-called photon conversion method, where we exploit the fact that a photon traversing our detector can undergo a conversion or pair creation to an plus/minus pair, and we can then measure these charged particle tracks of the electron and positron, and then from there reconstruct the photon. And this has the advantage that we are only limited by our tracking capabilities and therefore have a very good resolution as well as low PT reach. However, the whole method is of course limited by the probability of a photon to convert, which is roughly 8%. So then to measure the charged pions, we use the detectors I mentioned earlier. So our main tracking detectors, the ITS and the TPC. A particle traverses here, leaves a track. We apply some general selection criteria to ensure good tracking quality. And then we select particles originating from the primary vertex by cutting on the distance of closest approach to that vertex. And then we identify a track originating from a charged pion by cutting on the energy loss in this gas TPC detector, which is unique for each particle. This is what you can see in the plot here. And this is also how we identify the electrons for the photon conversion method I showed you earlier. So now that we have all the ingredients in place, we can start with the actual reconstruction. So first of all, of the pi0 or the eta, as I said, via the decay to 2 photons. And the idea really here is to use all the different techniques that we have to measure photons and combine them. So one could, for example, measure both photons with the photon conversion method, or one measures one photon with the photon conversion method and the other one with one of our calorimeters. Then we calculate the invariant mass of all possible photon pairs in a given event, and then simply select all the candidates in the vicinity of the nominal pi0 or eta mass as respective candidates. Then the same procedure again to get to the omega and the eta prime, again via the invariant mass, in this time of these triplets, so pi plus pi minus pi0 for the omega, pi plus pi minus eta for the eta prime. Then one ends up with an invariant mass distribution that looks something like this, what I show you in this plot in case of the omega. So an invariant mass distribution, a nice peak sitting on top of a combinatorial background. We describe the background using a second order polynomial, and then the signal is described using a Gaussian fit, where we obtain the raw yields by bin counting within 2 sigma of this Gaussian. But of course, it's not enough to simply obtain raw yields. One needs to do some corrections to then end up with a production cross-section. And mainly one needs to account for the limited acceptance of the detectors and also their limited efficiencies. And this is done using Pythia Monte Carlo events that are then piped through a Geant simulation of our full Alice detector. And then one ends up with these correction factors that you see in the plot on the right here, which is basically acceptance times efficiency, again, for an omega measurement for 4 different methods of measuring the photons. And I just put this here because it nicely outlines how each method has a different strength in a different region. So for example, the conversion method in black at low PT and the calorimeters at high PT. So this brings me to the first measurement that I want to show you, which is omega production in PP collisions at 7 TeV. And this was actually put on archive only this month and is now submitted to EPJC, so very fresh results. And the data set was recorded by ALICE in 2010 with roughly 400 million minimum bias events. And as I previously said, we used 4 different techniques to measure the photons. As you can see, all the 4 individual measurements are in agreement with each other, and they are then combined, taking into account the statistical and systematic uncertainties of the individual measurements. And then when one ends up with one combined measurement of the omega production cross-section, this is what you can see in black here. And this was done for the first time at mid rapidity at LHC energies. And we cover a momentum range of 2 to 17 GeV, and the systematic uncertainties are on the order of 20%, dominated by the signal extraction uncertainty. As you can see in the bottom panel here, we did several comparisons to theory. So first of all, two different Pythia tunes. In green, tune 4C, and in red, the Monash 2013 tune. You can see that the Monash tune manages to describe our data within the uncertainties over the whole momentum range, whereas the tune 4C overestimates the data. And this can mainly be attributed to the fact that the Monash tune includes more recent LHC results, and especially some parameters dealing with the production of vector mesons have been revised and lowered in the Monash tune. In comparison to a next to leading order calculation, this is what you can see in blue here. And this is quite an interesting one because they use a special dedicated model to describe the fragmentation into the whole vector meson nonet at the same time using a broken SU3 symmetry. And the model parameters have been tuned using PP data from RIG and the ± data from lab. And as you can see, it manages to describe it at low PT, however, then starts to overshoot with increasing momenta. We also had a look at the omega to pi0 ratio, which is somewhat a little bit motivated by something known as MT scaling, which is a phenomenological scaling rule that was previously observed at RIG and ISR. And what they observed was that you could describe multiple different particles with the same universal function of MT, and they would just differ by some constant normalization factor. So what you can see here is this ratio as a function of PT. This is why you see the slope here, and you see that it's constant above 2.5 GeV. It's in agreement with the measurement that were done at lower collision energy, so 262 GeV, and also with our theory predictions. What you see in blue is where we scaled a pi0 measurement with this normalization factor that we obtained to test sort of MT scaling. And what we find is, at least within our uncertainties, that we are compatible with MT scaling. And then I want to give you a quick sneak peek of what we are working on right now, which is omega and eta prime production in proton-proton collisions at 13 TeV. And this data set was recorded in 2016 to 2018. It's a really exciting data set because it offers significantly more minimum bias statistics than we previously had. So 1.6 billion minimum bias events versus 400 million that we had in 2010 for the measurement I showed you earlier. Also, the availability of triggers allows us to access a much higher PT reach than before. And also the LES detector has gotten several upgrades, for example, the decal I mentioned earlier. So two measurements. On the top right, you see one of these example bins for the omega measurement at 13 TeV. And this measurement is expected to cover a momentum range of 1.6 to 45 GeV. So you really see the triggers kicking in here with overall smaller uncertainties than we previously had. And the eta prime measurement will actually be the first measurement of its inclusive production cross-section, and it at LHC energies, and it will cover a momentum range, similar momentum range of 3 to 45 GeV. So stay tuned for these really exciting results. And this brings me to my summary. So what have we measured? I showed you a measurement of omega production in PP collisions at 7 TeV. That was done for the first time at mid rapidity at LHC energies. It was in agreement with the Pythia Monash tune and the NLO calculation at low PT. And I also gave you a sneak peek of the omega and eta prime measurement at 13 TeV collision energy, which really will provide insights into their production of an unprecedented momentum range with unprecedented uncertainties. Thank you for your attention.
So thanks to you, Florian, for this very nice talk. I really enjoyed that.
Thank
so
you.
are there questions or comments? Come on, guys. Well, I will start, but let's say I want to be followed. So now, very nice analysis of omega so that you are showing here, but in general also eta prime and pi zeros. with these photon methods. But I have a question about now the results that you have emphasized in your talk about the fact that the NLO calculation for large PT does not match the data. Now, you have advocated some coupling, general coupling of two vector mesons that have been tuned. But now, if I think about an NLO calculations, this is not really a calculation where single cross-section are tuned by hand according to, let's say, experimental data. Now, can you tell me a bit more?
I can maybe briefly elaborate a bit on the NLO. So what I meant with the model was tuned. So of course I'm not a theorist, but as far as I understood it from the paper, they have the model dealing with the fragmentation. There they have several free parameters that they tuned or obtained from their analysis of this RIG and lab data. And then the calculation they provide for us is basically the same model with unchanged parameters, but then fed into an NLO calculation at the proper center of mass energy and so on and so forth.
So you think really that this is let's say, fragmentation part for the vector meson production that then feeds in to the vector meson production that is out of tune, let's say, in the NLO calculation?
I mean, I wouldn't, I don't really know if I'm qualified to comment what leads to this excess at high PT. For example, we also see NLOs overestimating pi0 production, for example.
Yeah.
Yeah, one has to see what that actually is. It's difficult.
Okay, but most important is that the data are on the market and now can be...
Yes, exactly. This was the point I was trying to make.
Okay. So
if I may answer for the fragmentation part, so far we have always seen that once one includes the LHC data in the determination of the fragmentation functions and their evolution, that the NLO calculations in general get better. So as these fragmentation functions have quite some free parameters, it's most likely that these are, at least at high PT here, at fault.
Okay.
As they have been determined mostly at lower momentum.
Okay. So thanks a lot also for this answer. And we can move then to the next speaker, who is David Muller. And we'll talk about actually another initial state, annihilation of the plus and minus as source to have 6 and 7 pion final state. Oh my God, how many pions, David? So, okay, so for the bar collaboration, please start.
Yes, good morning. I will, as you say, talk about individual final states from a plus and minus annihilation that involve 5, 6, or 7 pions and possibly an eta meson as well. We get these from the initial state radiation method, which I'll describe. But first, we move on to slide 2. I've shown the total cross-section for E plus E minus goes to hadrons, which has been measured quite impressively over the past couple of decades, past 4 or 5 decades, sorry. And we think we understand this at high energies in terms of E plus E minus producing a quark-antiquark pair that shows up as jets in the detector. And we have a perturbative QTD description of that process that works quite well. At very low energy, on the other hand, all we see is a few resonances, but much more, and they've been measured quite well. And so what's really interesting now to me is the region in between, which I've expanded on slide 3 and normalized by the mu pair cross section. The rather dense red points are a sum of exclusive modes that have been measured so far. All the other data points are inclusive measurements, and the black solid line is the prediction of perturbative QCD. And what we basically see is that there's a lot going on here. There are several bumps and wiggles in the red points, other points all over the map, and there's quite a bit of physics still to be done here in this region where we're really transitioning from few body modes into jet-like modes, where we're going from not at all perturbative to fairly perturbative QCD. And I'll touch on a bunch of this physics, but the reason I'm giving a talk at a major conference is that theorists calculating the expectation for the anomalous magnetic moment of the muon and the running of the fine structure constant need the total cross-section as input to their calculations. And in this region, they have to make a bunch of assumptions which come along with a bunch of uncertainties. So to address this problem, we can build a collider to run in this region, or we can use the initial state radiation, which is diagrammed on slide 4. If the electron, or in this case, the positron, emits real photon before annihilating at a reduced center of mass energy, it can produce any system here labeled X that is allowed at that reduced energy. We know the cross-section for this process quite well in terms of the cross-section for the direct process. So one is a measurement of one is a measurement of the other. And so in principle, we can make measurements of cross-sections at all energies below our nominal center of mass energy in one experiment, which is a very nice thing. A couple of more features are shown in the event display on slide 5. We're looking along the beamline, and the large energy deposit in the lower right is what we consider to be the ISR photon. Recoiling against that is a system of 6 tracks in this particular event. We see the ISR photon in the detector about 10% of the time, and when we do, we get a really good measurement of a hadronic system because it's all in the detector. We don't have any funny acceptance effects around the edges. But furthermore, the system is boosted, so we see high energy particles in the detector. So we can measure everything, so we can measure all the kinematics well, even if we radiate all the way down to threshold. Of course, there are trade-offs in energy resolution. You need very high luminosity, but that's what the B factories were made for. Slide 6 shows a description of the Bauer experiment, which I won't go into in any detail. But the important things for this analysis is that we're able to detect photons and reconstruct pi zeros with high efficiency and resolution. And with the luminosity that we've accumulated at various energies, we have sort of millions of events in any region of the low energy spectrum that we want to look at. So on to slide 7, we've embarked on a program to measure all final states where, as defined by these 9 particles listed in the top left. The plot shows about a third of the measurements we've made so far, and just goes to show that there's a lot going on in this region between 1 and 3 JeV. In the last couple of years, we've added K-longs to our repertoire, and we've thus completed the 2, 3, and 4 meson final states. We've previously already measured 3 final states involving 6 mesons, and today we'll add a 4th, and along with our first 7 hadron final states. So on to the analysis, slide 8, which is conceptually simple, but rather compute intensive. We look for events that contain a high energy photon, exactly the right number of charged tracks, and a bunch of photons. We have to set the photon threshold quite low to get all of the signal photons. We combine photons in pairs that might be somewhere close to a pi zero. And then for every possible combination of 2 or 3 of those pairs and 2 additional photons, we do a constrained kinematic fit to the full event of that combination plus the charge tracks and the ISR photon. Take the one with the best chi-squared. And that sounds simple, but we also test a bunch of other hypotheses, see if we find any better chi-squareds. And these chi-squared distributions are really valuable in getting a handle on most of our backgrounds. So after that selection, we get the plots of the invariant mass of the unconstrained photon pair on slide 9. And you can see nice peaks for the pi zero and eta. The pi zero peak looks funny because we've intentionally chosen the worst pi zero to plot. But still, this distribution is predictable, and we can do fits to these distributions to get the number of detected events in whatever bins we like. And this procedure gets rid of all of our backgrounds except for one. That one is the electron-positron annihilation into 2 jets at our nominal center of mass energy, where one jet is mostly a pi zero. And the way that pi zero decays is mostly a hard photon. We can't suppress that, but we can measure it in the data. On slide 10, the blue plot shows the invariant mass distribution when we combine our ISR photon with a soft photon in the event. We see a bump around the pi0 mass that wouldn't be there in the absence of this background. And we can use this to normalize a simulation of that fixed energy process. The two rather busy plots on the bottom just show that we've thought a lot about our efficiency. And what's nice is that it does not seem to depend much on the different sub-processes that make up this final state. And so we're able to use a nice average, which is shown as the black line, as our efficiency. Putting all of this together, we obtain the cross-section shown on slide 11, the first for the four modes we're talking about. The first thing you notice is nice big signals for the J psi, which I'll come back to later. An interesting feature of almost all our cross sections is that they're very small between threshold and about 1.5 or 2 times threshold. And then they shoot up, in this case, to about to a nanobarn or 2 in the case of the all pion modes, and about 1/10 of that for the modes involving an eta. And then they tail off with increasing energy at some rate. So these are important contributions to the total cross section, a few percent each, 3% total, and make a nice addition to our knowledge. One interesting thing about the 6 pion cross section is shown on slide 12, where I compare with our previously measured cross sections for 6 charged pions and 4 charged pions and 2 neutral pions. In both of those cases, there's a dip in the cross section right around proton-antiproton threshold that is not understood. And well, it's still not understood. I'm not sure if this new measurement helps or not. Looking inside the 6 pion mode, slide 13, we observe a whole bunch of stuff. We observe several 4-body modes, eta, omega, and phi plus 3 pions, a 2-body mode, eta, omega. The plots on the right just show the signals for some of these modes. And we see a bunch of modes involving rows, although they're very hard to disentangle. And this is a very rich substructure, and it's quite similar to what we saw in the mode with 4 charged and 2 neutral pions. But another mystery that still holds is that we did not see much structure in the 6 charged pion mode. We're able to extract cross-section for 3 of these modes, and those are shown on the next slide. The eta pi plus pi minus pi 0 and the eta omega cross-sections are consistent with previous measurements that show a nice substantial bump-like thing between 1.5 and 2 JeV. And then we see a falling cross-section at higher energies. We've also got a first measurement of the omega pi plus pi minus pi 0 cross-section. We can't really measure any of the row cross-sections, but we can tell that they don't kick in until about 2 JeV. And what's interesting is that the modes that we've measured really account for almost the entire cross-section up to 2.9 JeV. And these are not what you think of as jetty events. The omega eta is a 2-body mode. The 4-body modes, we're not used to thinking of jets as containing only 2 particles. So we're really not into the jetty regime here, even at 3 JeV. We see a very similar structure in the 7 pion mode. In fact, this slide is almost a copy of the one before last for the pi 0 added to every decay mode. So this is looking a bit more jet-like in some of the modes, but the omega pi 0 eta is still a 3-body mode. And the eta and 4 charged pion mode really seems to be composed of 3 and 4 body intermediate states. So again, we have a very rich substructure that's not particularly jetty. We can extract cross-sections, again, shown on figure 16, slide 16, and we have several that are consistent with our previous measurements, important to check, and a new measurement of the omega pi plus pi minus pi 0 cross-section. Finally, if we look at the charmonium region, slide 17, we see a large peak for the J psi on the two plots on the left, which are 6 and 7 pion modes, and also in several of the submodes, which are the smaller plots on the right. It's kind of cute that we're also seeing the psi 2s, but these decays are into 6 and 7 pions are largely dipion returns to the J psi. And so it's kind of fun. But we can, from these data, extract branching fractions shown in the table on slide 18 for the J psi and the psi 2s into several modes. Many of these are measured for the first time, and several of the PDG entries are basically our measurements from other decay modes, or other final states rather. So to summarize, we're still around doing low energy hadron physics. I hope you've enjoyed seeing lots and lots of pions on your screen and the occasional atom meson, and making up lots of substructure. Much more is possible, and I hope we'll be showing you that in the near future.
Thanks a lot for your talk. So I will also start also in this case with a question, and I was thinking about many pion strong interactions. So because, I mean, it's true that we know very well the scattering parameter for 2 pion final state and also partially for 3 pions, but actually nothing excludes that there is also some residual strong interaction also for many pion, and I mean strong interaction, not the Coulomb. Would these impact on your measurement and on the spectral shape you look at and on your analysis, or is something which is completely negligible and of no importance?
I don't actually, so in some of our measurements that is important. For example, in our proton antiproton measurement at energy. I think the question is the other way around. Do you see anything in our data that
can help to constrain these parameters? Yeah, maybe. Yeah.
Yeah, I mean, we haven't in general, we haven't taken this into account. No.
Because, I mean, this is actually a very important point, I think, for low energy QCD, that, I mean, even pion has exchange boson in all possible reaction involving hadrons. I mean, they are under control when you have 1, 2 pions, but if you have 3 or 4, I mean, this is just like completely complicated, right? So maybe this data can help in that direction, yeah? Since you have so many pions, especially in those cases in which you have 4 neutral and only 2 charged, and then you don't have long range Coulomb interactions. Okay, so I don't see any other question or comments. So thank you very much again for your talk. And then we move to the next one, to Sushanta.
Hi, can you hear me?
Yes, very well.
Okay, let me share the screen.
And you will talk about topological study of light flavor hadron production in high multiplicity PP collision with Alice.
Okay, so can you see the slides?
Yes, very good. So go ahead.
Okay. Hello, everyone. I'm Sushant Tripathi. So on behalf of Alice collaboration, I would present the topological studies of light flavor hadron production in high multiplicity PP collisions with Alice at the LHC. So as you might know that the recent measurements at the LHC have revealed that small collision systems exhibit a galactic-like behavior, which were formerly thought to be a distinctive feature of heavy ion collisions. So some of these collective-like behavior are like the restructure in high multiplicity PP collisions, which were thought to be the feature observed in heavy ion collision due to collectivity. So we observe the straightness enhancement in high multiplicity PP and P-led collisions are very similar to the lead ones. And we observe similar features of variant to Mason ratios in like for P/Pi ratio in PP, P-led and P-led and lead collisions in different multiplicity classes. So to remind you that traditionally we use the small system as the baseline for the study of possible formation of QZP in heavy ion collisions. So so far the origin of the collective like behavior in small collision systems are still under debate. So to understand this, let us discuss two scenarios in this talk. So we will try to use event-safe observables to isolate different physics regimes, soft versus hard. And all the measured results will be compared to the microscopic and macroscopic models like PTI and LiPo. So before going to the results, let me briefly explain the ALICE detector. So you have already heard in previous ALICE talks about the ALICE detector. So here I will highlight the detectors which I used for this analysis. So we have taken the help of 4 detector subsystems, namely the inner tracking system, which I used for trigger, tracking, and vertex purpose. And it is also used for the multiplicity estimation as well. So in ALICE terminology, we call it as CL1 estimator. So if we measure the particle in mid rapidity and use this estimator, then it would give an insight to autocorrelation effects. Then we take the help of time projection chamber for tracking and particle identification. The time of flight detector is also used for the particle identification. And we take the help of 2 forward detectors, V0A and V0C for the trigger and multiplicity estimation as well. So in ALICE terminology, we call it as V0M estimator. And if we measure the particle production in mid rapidity using this estimator, then it would be more robust against the autocorrelations. So with this, let us move to the first part of the results. So here in this part, I will show the results for identify particle production as a function of transverse sphericity. So you might know that the transverse sphericity has a very nice capability to discriminate the events based on hard and soft processes. So one can obtain the sphericity using this formula. And if the sphericity is tending to 0, then we call it as ZT events. And we expect that a back-to-back structure in the transverse plane. And if sphericity is tending to 1, then we would expect an isotropic event. And in those events, we would expect an enhancement of underlying events. So using this sphericity, we obtain the particle PT spectra, identify particle PT spectra in high multiplicity collisions at 13 TeV. So at first, let us look at the V0M, the results we're using V0M estimator. So here we have the PT spectra for pion in different sphericity classes, sphericity integrated class, isotropic and ZT ones. And the lower plot show the ratio of isotropic and ZT ones to the sphericity integrated one. So you see that there is a clear dependence of the PT spectra on sphericity. We have also the results for the other identified particles like kaons, protons, and Xi. So if you have a look at pion, kaon, and proton, we see a clear distinct crossing point of ZT events to the isotropic ones. For Xi, we could not go very far in PT range. So in the major PT range, we do not observe any convergence to unity for the isotropic and ZT ones. And the result seems flat around unity. So let us look at how the results behave in the CL1 estimator, which is the mid rapidity estimator. So here in this case for pion, kaon, and proton, we see that the ZT events dominate at a lower PT bin compared to the V0M triggered events. And for the Xi, unlike the previous case, here we observe a convergence to unity. So when compared to the 2 estimators, so we observe that the V0M triggered isotropic and ZT events have larger multiplicity difference. However, when we trigger with the mid rapidity estimator, we see that the events are disentangled more accurately in a very small multiplicity gap. So with this, so let us look at the identified particle ratios as a function of sphericity. So here we have the results for Py-pi ratio in different sphericity classes. And then in the lower panel, we have the double ratios to the sphericity integrated one. So here we see that the Py-pi ratio is enhanced at intermediate PT and isotropic events, which is somewhat reminiscent of the similar effect in leaded collisions, which I have shown you in the motivation slides. Then we have also the results for Xi-pi ratio as a function of PT. So when we look at the Xi-pi ratio, we observe that that one can really increase or decrease the straightness enhancement with the selection of the transverse sphericity. As you can see that the isotropic events are higher in Xi-pi ratio and compared to the ZT ones. So And all these results are compared with models like PTI-8 and EPOS LSC. So in general, if you see in the particle ratios, the models doesn't describe the data. However, they do, the trend is somewhat explained by the models in the double ratios. And when we look at the PY ratio, we see that the PTI-8 is closer to unity compared to the EPOS LSC. And for Xi-pi ratio, both the models have good agreement with the data. So then let us look at the second part. So we will have a look at the charge particle production as a function of RT. RT is nothing but the relative transverse activity classifier, which is another event step observer. So in this framework, we will try to look for the jet quenching effects in small collision systems. So RT is nothing but the charge particle multiplicity in the transverse region and divided by the average number of charge particle multiplicity in the transverse region. So it is a very useful tool as we can, using RT, we can change the transverse activity with the low and high transverse activity, and we can study the collective effects. And this will also give an insight to the autocorrelation effects if we measure the particle production in the transverse region, as the RT is also calculated in the transverse region. For the calculation of RT, we need to ensure a PT leading cut. The PT leading cut for our analysis are determined with the two effects. So as we will look for the jet quenching effects in using RT, so we have chosen this particular PT leading cut. And in this PT leading cut, we also see that the number density as a function of PT in the transverse region remains nearly constant. So with RT, we will also look at the PT spectra in PP collisions at 5T for the charged particles. So here we have the results for 3 different topological regions, near, away, and transverse side. In the upper panel, we have the PT spectra for different RT bins. And in the lower panel, we have the ratio of the PT spectra to the 0 to 5 RT spectra. In the transverse region, we see that with increasing in RT, we have the rise of PT spectra with RT. However, the behavior is completely different in near and away side, where we see that in high PT range, the PT spectra is more or less RT independent. However, we see a small dependence on the RT in the low PT bands. So all these results are compared with PTI-8 and EPOS LSC. So what we observe is both the models explain the data qualitatively. However, there is some quantitative disagreement, which we hope it will help to constrain the MC models. So in this framework, we'll look for the jet quenching effects in small collision systems. So for this purpose, we take the help of this observable called IPP, IP-led, and I-led. So this is nothing but the total integrated yield in different collision systems subtracted by the yield in transverse side. And this is scaled with the same thing in the PP minimum bias collisions. So here we have the results of this observable as a function of N-char transverse for the near and away side. So if we see any kind of suppression of this observable in the away side, then it would indicate the presence of jet quenching effects. So indeed, we observe significant suppression in central lead-lead collisions. However, when we go towards the small systems, we do not observe any kind of suppression in the away side. So this would be an indication that there is no hint of jet quenching in small collision systems. So with this, I will summarize my talk. Hope I have convinced you that the transverse velocity and relative transverse activity classifier do very nice job to distinguish the events based on hard and soft processes. And the results, the measured results and comparison with models like PTI-8 and EPOS LSC will constrain the MC models. And in contrast to lead-lead collisions, so we do not observe any kind of suppression in the away side for the small collision systems. So this would indication of no hint of jet quenching in small collision systems. So we have also some additional results with due to time constraint, I could not put in the main slide. So you can have a look into the backup slides. So thank you very much for your attention.
So thank to you, Sushanta, for these very nice results. And I have a question, and if you could go to slide number 13. where you showed the Xi to pion ratio and the antiproton to pion ratio is a function of, let's say, the sphericity. I mean, cut, jetty, and isotropic. Now, I understand that, let's say, the measurement of Xi to pion ratio in the two selections, for the two selections, are in agreement with Monte Carlo, but I do not understand the physics behind that. So why in one case it goes up and in the other goes down? Could you maybe explain me this a bit better?
Actually, so if using transverse sphericity, we are distinguishing the events based on hard and soft processes, right? So for isotropic, we would expect more, enhancement of underlying events, and jetty ones is more like back-to-back structure. So, if we expect a collective like effects like a straightness enhancement, so that would be enhanced. We expect it would be happening in the more in isotropic events rather than the jetty events, right?
Because you expect this enhancement to be, let's say, part of the soft physics and not of the hard scattering.
Yeah.
I see. That's why then. While in the jetty, let's say, this is exactly also what you see, right?
Yeah. In the PVI ratio also you see the similar thing.
Yeah, the same is, similar to the antiproton to pion ratio. Okay, yes. Other question or comments? Okay, this is not the case, so thanks a lot, Shanta, for your talk. And then we move to the next speaker, who is also the last speaker. And this is Amse Kampur, who will talk about QCD analysis for the transverse momentum dependent on fragmentation function. And again, back to a plus minus annihilation. Hamze, do you hear me?
Yes, can you hear me?
Yeah.
Can you see my slide?
Perfect, yes. You just go to presentation mode.
Okay.
Perfect, go ahead.
First of all, I'd like to thank the organizer for this interesting virtual conference. Today, I'm going to talk about the transverse momentum dependence of charged pion and charged cone and proton and antiproton fragmentation function from electron-positron annihilation process. This talk is based on the following publication, and I'm not going to talk about the detail, and you can find the detail of the analysis and the study in this paper. And I'm going to talk about some main points and results and findings. In this study, we determined for the first time the transverse momentum dependent of unpolarized fragmentation function from electron-positron annihilation data. For the data, we used the most recent TMD production cross-section of charged pion and charged cone and proton and antiproton measured in inclusive electron-positron collision by Bell experiment at KEKB. This is the outline of my talk. I will talk about the hadronization, and especially I will talk about the single inclusive electron-positron annihilation process. Then I talk about the semi-inclusive and deep inelastic scattering, and also about single inclusive hadron collision. Then I will discuss about the transverse momentum dependence part and distribution function, and also TMD fragmentation function. Then I will present the method of our analysis, the Bell collaboration data sets, the factorization, the fitting methods, and the kinematic cuts and other things. And then I will present the results and the main results and finding of our analysis. The hadronization process means that it turns partons produced in hadron scattering reactions into a physical, colorless, non-perturbative hadronic bound state that detected in experiment. It can be a light or heavy hadron, for example. And the process with an observed hadron in the final states can be described in terms of two important terms. The first one is the perturbative hard scattering cross-section, and the second one is the non-perturbative but universal functions. These non-perturbative functions need to be determined from QCD photo data. They are, for example, the parton distribution functions, or for example, the polarized parton distribution function or nuclear parton distribution function. These functions accounting for the partonic structure of hadrons in initial states before the hard interaction. And the second one, and the important one, is the fragmentation function. It can be, for example, the transverse momentum fragmentation function. It encodes the details of the subsequent hadronization process. Fragmentation function are essential ingredients for the present and also for the future hadron colliders, such as, for example, high luminosity phase or high energy phase of LHC, or large electron hadron collider, or future high luminosity or high energy collider. This is an essential ingredients for its theory prediction in these collider. And also fragmentation function are basic ingredient for the calculation of the production of high transverse momentum particles at collider energies within the perturbative QCD. This is the proton-proton collision, and this is the fragmentation function. A parton is a fragmentation to a hadron. And also this is the semi-inclusive deep inelastic scattering in double hadron production, as one can see here, the quark fragments to the two hadron. A precise determination of such function, along with the experimental uncertainties, had become an active topic for many hard processes. For example, in this process that have been measured at Hera Collider, which is correspond to the DS0 plus minus production, I mean heavy hadron production at Hera, or for example, the transverse momentum dependent production cross-section of charged pion, kaon, and proton and antiproton at Bell experiments. And also it can be the proton-proton collision at a hadron collider such as LHC. The cross-section for such process can be obtained by the ordinary parton distribution function and also the transverse momentum dependent parton fragmentation function. And also for these two processes, as can see here, the cross-section can be expressed in terms of transverse momentum distribution dependent fragmentation function. And also in proton-proton collision, we have two parton distribution and a hard scattering cross-section, and also fragmentation function. Okay, let's move to the transverse momentum dependent parton distribution functions. This diagram describes the relevant momenta involved in a semi-inclusive DIS event. In this diagram, one can see a photon, a virtual photon defining in the reference axis strikes a parton inside the proton, The parton has a transverse momentum of KT that's not measured. And also these struck parton could fragments into a hadron will acquire further transverse momentum PT. The total measured transverse momentum of the final hadron is PhD, as you can see here. We have two universal functions here. The first one is the unpolarized TMD parton distribution function that describes these vertices. And another one is the unpolarized transverse momentum distribution fragmentation function that describes these vertices and a parton into a hadron. These functions depend on the fractional energy carried by the hadron, but also this function, in this function, KT is the transverse momentum of the parton with respect to parent hadrons, and PAT is the transverse momentum of the produced hadron with respect to the parent parton. Okay, in this analysis study, we plan to determine the transverse momentum dependent fragmentation function from the electron-positron collision, not from the semi-inclusive process. Okay, most recently, the Bell collaboration in this conference announced that they measured the transverse momentum dependent production cross-section of charged pions, cones, and proton produced in an inclusive electron-positron annihilation process. We have used these data set to extract the transverse momentum distribution fragmentation function. This is the published paper by Bell collaboration. They report the production cross-section of charged pion, cone, and proton as a function of three independent parameters. The first one is the fractional energy, and the second one is the event shape variable called thrust, and the second one is the transverse momentum with respect to the thrust axis. These data sets correspond to data sample of 558 inverse femtobarn data sample, and has been measured by Bell detector at the KE-KB asymmetric energy electron-positron collider. And I refer the audience for the detector setup and reconstruction criteria and other things to this publication. One of the important things, topics, or that this measurement shows that the Gaussian functional form could describe well the transverse momentum dependence at small transverse momentum. So we exactly follow the findings and consider a Gaussian functional form to determine the TMD fragmentation of function of a charge pion, cone, and proton and antiproton. As I said, the data sample is 558 inverse femtobar collected by Bell detector. The data has been measured as a differential cross-section, which depends on fractional energy, and also to the transverse momentum PAT, and also to the thrust value T. Experimentally, the transverse momentum of the hadron is calculated relative to thrust axis, which could maximize the event variable thrust T. Okay, The data sets that have been measured by Bell collaboration is for several beams of Z and also beams of transverse momentum, and also 6 beams of thrust values. The main goal of this measurement is the extraction of Hadron cross-section from light, UDS and charm pair events. This distribution shows the event per thrust for a selected Hadron sample for different sub-process. But as one can see here, the blue one, charm, and the red one, UDS, peak around the thrust value between 0.85 to 0.9. So they decided to present the data sample and also all the distribution analysis studies for this particular value of thrust. And also we restrict ourselves in the analysis to the thrust value between 0.58 to 0.9. This is exactly the data set that we have used in our study. This is the first direct transverse momentum dependent single hadron production cross-section in electron-positron collision. And we extract for the first time the transverse momentum fragmentation function using these data sets. These data sets correspond to the pion, charged cone, and proton and antiproton production. It is correspond to these thrust values, and also for different beams of Z momentum fraction, and also different value for PHT. As one can see here, for larger value of PHT and also for some value for Z, the data come with large uncertainty and error. So we have to exclude these data set from the analysis. We perform and investigate a K-square scan to remove and exclude this data set from the analysis. Okay, let's move to factorization of TMD fragmentation function. Factorization of TMD is that for a process of electron-positron 2 hadron X process, one can write the differential cross-section as a term of total inclusive hadron cross-section, and also the two-term. It means that the transverse momentum fragmentation function. The transverse momentum fragmentation function has have two terms. The first term is the unpolarized collinear fragmentation function, and the second one is correspond to the TMD dependent part. So we consider the following function for the transverse momentum dependent fragmentation function, and for the unpolarized collinear fragmentation function, we have used the most recent study by the NFF collaboration, and we consider a functional form for the second term and extract this term from QCD fit2 data. This table shows different phenomenology groups that determine the fragmentation function. We have used the NFF fragmentation function for the baseline fragmentation function in this equation. And they use the Monte Carlo method and neural network and obtain the fragmentation function of charged pion, cone, and proton in zero mass variable flavor number scheme and up to next to leading order perturbative QCD. Okay, as I mentioned before, as the collaboration also indicates in their measurements, a Gaussian form for the TMD fragmentation function could describe these data sets. We exactly follow their measurement and also follow these two studies. Consider the following functional form for the TMD fragmentation function. PTS square is considered to be as a function of 3 independent fit parameters, and our input scale is considered to be 5 GeV. We define a KS square in order to determine these 3 independent fit parameters. Epsilon I is the experimental values. This is a theoretical one. This is the error of the data. And minimization has been done by the CERN program library. Okay, as I mentioned before, we performed a K-square scan to remove and exclude the data with a large uncertainty. This plot shows our K-square scanning for the PHET, and we exclude the data for PHET bigger than PHET max, where we exclude the data from our feeds. And also we perform the same K-square scanning for the Z maximum in order to exclude the data, the large Z maximum data. This plot shows the sensitivity of K-square over degree of freedom to the Z maximum. Finally, we have used the following data sets in our QCD study for the pion and kaon and proton and antiproton. And this is the Z range, momentum fraction range, and this is the transverse momentum range for the pion, kaon, and proton. And this is the remaining data sample in our feed, and this is the K-square over degree of freedom. As one can see, it shows that the data theory agreement should be well. And this is the parameters that we consider in our Gaussian functional form for the TMD fragmentation function. This is the fit parameter that we obtain from QCD fit2 Bell collaboration data. Okay, let's move to the results. These plots show a comparison between the theory prediction for the transverse momentum dependent production of charged pion and the data from the Bell collaboration. As one can see here, the data theory agreements are acceptable. And this is the result for the kaon, and again, this is the result for the proton. Okay, let's move to the distribution of PTS square. These three plots shows the distribution of PTS square as a function of Z. And as I mentioned before, the alpha, beta, and gamma need to be extracted from fit2 data. Okay, let's comment some about future high energy collider. Future colliders such as LHC, Large Hadron Electron Collider, or Electron Ion Collider, or high luminosity and high energy FCC would offer unique possibilities to reach the ultimate precision in the Barton distribution function and also fragmentation function determination by probing the kinematic region, which are far from the reach of current experiment at LHC. This is the coverage of the kinematic plane in deep inelastic lepton-proton scattering from FCC-HE and also from the LHEC to be compared to the HERA and some other old fixed target experiments. And finally, future circulator collider FCC. This is a large high energy and high luminosity collider with the aim of reaching collision energy of 100 TeV, the phenomenology of Parton distribution function and also fragmentation function should be very rich in such extreme energy. And okay, let's move to summary and conclusion. Most recently, Bell collaboration at KEKB published the first measurement of differential cross-section for the charged pion, kaon, and proton and antiproton. These data sets are only available, observable in SI process, which we used for the first time to determine the unpolarized transverse momentum fragmentation function for charged pion, charged kaon, and proton and antiproton from QC-Fit2 data. This analysis is restricted to the electron-positron alienation process, and hence another possible area of future research would be to investigate the effect of another source of information, for example, see this process on the transverse momentum distribution fragmentation function. Okay, I would like to thanks again the organizer of ICHEP conference and your attention.
Okay, thank to you for this nice talk. I actually have a question about the results that you show in the end, because if you go to the slides showing the results for kaon and pi, yeah, exactly here. For proton, the theoretical predictions, they reach out up to 1 GeV, while for kaon, they stop before, they stop at 0.47.
Yes, it's exactly as I mentioned here. We perform a chi-square scan to determine the best PHET maximum cut for the pion, kaon, and proton. The difference you can see here because the cut for the PHET maximum cut for pion, proton, and kaon are different.
But where does it come from, the fact that the cutoff is different? Just because if you would fit to a larger momentum, the chi-square...
Yes, exactly. Yes, exactly.
But the physics behind that, how can we identify the reason of this cutoff? I do not understand exactly where this comes from.
But in our analysis, we perform a chi-square scan. And I should mention here that the Bell collaboration performed the analysis for 0 to 1 for PHET GeV, but in our study, like other phenomenological study, we perform a chi-square scan to find the best PHET maximum for the analysis.
Yeah, okay, I understand. Thank you.
You're welcome.
So I think that there are no other questions, at least I don't see any. So I would like to thank you. So
thank you very much
for your talk, and also all the people that talked in this very tough session that took now until 9:30, and also to the people who stayed connected. So thank you to all of you speakers and also attendees, and then we meet again tomorrow for another strong interaction. Okay, so good day, depending where you are. Goodbye. Bye-bye.
Bye.